because the area is okay, but the sigma is not constant. So you must find an area. Please notice this is an important point. You must find an area, small enough area, for which you can make this assumption. Sigma is constant. Okay, so we are going to assume lambda is constant for an interval. Sigma is constant for an interval. So for sigma, obviously, it will be constant over a dA. If I do rho, it will be constant over a dV. Now you must be very sure that for that dV or that dA or that dL, lambda is constant. Okay, or sigma is constant. Okay, so if I am assuming that for this little piece it is constant, then I can say for this piece that dq is sigma dA for this tiny dA. Now if I go here, this is going to be a different dA and a different sigma. So you will take again for this fellow sigma dA, except the sigma is different from that sigma, the dA is different from that dA. But if I did this for all such pieces and I didn't lose any piece in the middle, like if I did all this and left off those pieces, then it's not counted. I must make sure I add every such portion that has been missed out, but no portion has been double counted. No, you can't do that. This is not allowed. Okay, that means if I integrate this, we call this addition, integration. So if I integrate it over every part, so the entire area, in such a way, no part has been double counted and no part has been left out. So everything has been counted once and only once. So sigma dA is actually dq. People start focusing on the integral too early. What I want you to understand is that this is the important thing. This fellow has a charge dq, which is sigma dA. Concentrate on dq, forget the sigma dA. I mean, this is sigma dA, forget the integral of sigma dA. You will need to do the integral to find the charge, but many times dq will produce a potential here. Now the potential is not the summation of the charge. Potential will basically dq will produce a dV. How much will that be? K dq by R. But this guy will produce also a potential there. It's a different dq. It's a different R, R1, dq1. Potential will be K dq1 by R1. You will need to add up this. You don't need to add up dq in this case because each dq produces a potential, right? So remember, if I want to find charge, then I want to add up dq's. If I want to find potential, I have to add up dv's. Okay, but who is going to produce your dv? dq. So do you need to know what dq is? Absolutely. In fact, that is more important than knowing q. Q is, if somebody asks you for q, it's fine. But for finding every point, what is the potential or what is the electric field, you need to know dq. So what is dq? At this location, there is, think of it like, see, we are now going to continuous charge distribution, right? Now instead of having many point charges, you have a slightly larger surface which you are going to call like a point charge. Then you have here another point charge. Think of it as you have another point charge, another point charge, another point charge. Now there are billions and billions of such point charges. Now they are going to probably produce something there, and what integration does is to provide us a cool way of adding up all of these effects. That's just a mathematical trick. But the principle is, at every point, think of it like a point charge. How much is the size of the point charge? dq, very tiny amount. So what will be its effect far away? Very small, because it's a tiny amount of charge. How much is the charge? Sigma dA or lambda dL, or in the case where I have, let us say, a three-dimensional surface. Okay, now let's imagine that this is a three-dimensional surface. At this point, I might have a rho. I will have a different rho here. So this is a three-dimensional surface. So I'll just mark it like that. Okay, now this is a small blob. This is a different small blob. This has rho 1, this has rho 2. Now rho is the charge density at that location. What does that mean? That for each point, like each point around this, you take a small dV which you can assume. What is the assumption? For that dV, hopefully rho 1 is constant, nearly constant. Okay, that's important. The fact that if if for example rho was changing rapidly, you will have to make dV really small. Okay, the more rapidly it changes, the smaller is the dV. So what is the charge here? What is the dq here? Rho 1 times dV. We stop writing rho 1, we will just write rho. Rho will be a function of the point. So this itself will have an x comma y comma z. Or if it was a surface, typically it will have an x comma y. So usually what will happen is that when you put sigma, sigma actually will be a function of x comma y. When you do dA, dA will be a function of x comma y. This will give me dq where? For that small area at x comma y. If I go here, I'll get a different area and a different charge. So you are basically breaking it up into lots of small pieces. Each piece is a charge dq. If you want to find q, you just do this integral. So is the logic of this clear? So the basic idea behind all of this is that you can assume, though lambda or sigma or whatever is varying, you can assume that it is pretty continuous around a very small portion. The small portion could be a length, small portion could be an area. Remember, whenever you get a sigma, multiply by an area. It may be a tiny area, it may be almost zero, but you are multiplying by an area, because sigma times that little tiny area will give you a little charge. Similarly, lambda multiply by a little length. For a rho, you are multiplying by a little volume. Okay, and then how to integrate, that's something that we are going to learn, but I hope everybody is clear about this. So therefore, you don't write lambda into L, you are going to write integral lambda dl. Over what limits? Over the entire length. How to cut it up, how to join it, how to connect. This is the symbol for joining. This tells you that it has been cut up. So you are cutting it up and then you are joining. Cutting it up in an exclusive way, that means once only, and counting everything, but only once. And then similarly you may end up with sigma dA, or you will end up with a rho dA. So all of this will be the charge. So this is rho dV. Okay, so this is rho dV, sigma dA and lambda dl. Now to produce all this, remember you have to start with a dq, and dq is lambda dl, sigma dA or rho dV. Okay, so before we get down to learning how to actually calculate it for different cases, what we will do is learn first how to first cut it up into lengths and areas and volumes, and how to add them up. Okay, because this is a step that is one step away from doing integral dA. Like suppose I tell you, you want to find the area of this fellow. How will you find the area for this fellow? Just simply cut it up into small, small pieces. Calculus tells us that you can just do all of this. You can cut it up like that. Now this is a tiny area. So if I find that area and then this area and this area and this area, I just add it up. So therefore, dA integral gives me A. Now what we are saying is when you cut it up into small, small areas, for that little tiny area, you can also have a dq. So if I put a sigma inside that, then I will be able to add up dq's, which will give me q. But you see, that's one step away from adding up just the area, right? So how to find area is the first question. How to find volume is the first question. How to find length for a curved surface, first of all. Once you know that, which is the basic part of integration, then we can look at how to find charges. Then the next step will be, once you know how to find dq and the charge total, then you say, well, this charge produces a potential. How to find potential? Because this guy will produce a potential, this guy will produce a potential, this guy will produce a potential. Add up the potentials, don't add up the charge. Add up the areas. Now we are saying, no, don't add up the areas. Add up the charge at this area. That will be sigma dA. This will produce charge. So what am I doing? Instead of cutting it up and just simply adding the areas, I am going to cut it up, find the charge there and add up the charge. When I get to potential, I will say, no, cut it up like you are cutting up area. But then find the charge there, but don't add up the charge. This charge will produce a potential there. We'll call it dV. Now similarly, this charge will produce a potential there, which will be also called dV, but different dV. Now you're going to add up all of the dVs. You're not going to add up all the charges. Later when we do electric fields, then you say, okay, this guy is going to produce an electric field. Now that electric field will have components. Take components, then add it up. So you see that all of these actually build from here. This is the easiest problem, next level problem. and then finding potential is the third level problem, and so on. So we'll get started with how to find the sum of, just to look at very quick idea of areas. You will learn a lot of that in calculus, but we are going to just learn a little bit so you know what to do for solving problems here. Just keep in mind, but when you're finding areas, I don't even have the extra problem of how to cut it in such a way that the sigma is constant. I don't have to worry about it because I don't care. I'll just cut it however I want. Whereas when you're looking at charge, you have to make this assumption. So you want to cut it in nice ways such that for that nice area you have taken, sigma is constant, or at least reasonably constant. For the nice area that you have taken, lambda is constant. Sorry, nice length that you have taken, lambda is constant. For volume, rho is constant. So those are also extra conditions that we'll have to think about. So when we get to problems, we'll understand that. Cut. எவ்வளவு நேரம் போச்சு? 10 minutes சொன்ன?
It's okay, Balaji.
நல்லா வந்தது அது?
சூப்பரா வந்திருக்கு. I'm so happy with it. The way you interlinked the integration part இதையும் நீங்க சொன்னது, it was fantabulous.
எந்த பார்ட் சொல்ற?
The slope வச்சு நீங்க interlink பண்ணி இதுக்கு நான் calculate பண்ண வந்தது.
அது ஓகே. இது பட் ரொம்ப கொஞ்சம் கச்ச கச்சன்னு வந்துச்சு.
இல்ல, it was very much clear.
கிளியரா?
ரொம்பவே கிளியரா வந்திருக்கு. நான் linear chart
நான் ரோக்கெல்லாம் பண்ணலையே.
இல்ல, இது போறோம் Balaji. ரொம்ப இதுக்கு மேல பண்ண வேண்டாம்.
அவ்வளவுதானா?
Like too much போடாது.
சரி, ஓகே. இப்போ எரேஸ் பண்ணுங்க. ஒரே ஒரு செகண்ட் அந்த ஷீட்டை காட்டு. கிளாஸ்ல பண்ணனே. கிளாஸ்ல பண்ணது இன்னுமே வரலையா அப்போ?
இல்ல, கிளாஸ்ல பண்ணது அந்த கோஹெரன்ஸ் வந்து இந்த அளவுக்கு டீப்பரா இல்ல.
பக்கா வருதா? வெரி குட்.
நீங்க இதையே செக் பண்ணிட்டீங்களா?
பக்கா குவாலிட்டி.
இதுவேவா?
இது நம்ம 480 வீடியோ அப்லோட் பண்ணல, அது ஒண்ணுமே கிடையாது. இதுதான் ஹை குவாலிட்டி.
இப்போ போயிட்டு இருக்கோம்ல அங்க.
இப்போ இல்ல, முடிஞ்சிருச்சு. ரொம்ப டிலே ஆகுது. இப்போதான் முடிச்சு தான் வந்திருக்கு.
சார்ஜ் ஹஸ் நோ வால்யூம்.
ஸ்பீடு தான், அது கொஞ்சம் ஸ்டார்டிங் தான்.
இது இப்போ இதுதான் பண்ணணும். சரி, ஆமாம், குரூப்பில் போட்டுருவோம். இப்போ போட மாட்டோம். இப்போ போட்டுருவோம். அதே லிங்க் தானே? பர்மனெண்ட்டாக அதே லிங்க்கா? பர்மனெண்ட்டாக அதே லிங்க்கா?
இப்போ ஓபன்லனா அதே லிங்க் தான் வரும். சேஞ்ச் சேம்.
பட் இப்போ ஓப்பன்னா பர்மனெண்ட்டாக வந்துட்டே இருக்கும்ல?
இப்போ இது போயிட்டு தான் இருக்கு. ஓப்பனா கட் ஆயிடும்.
அப்போ லிங்க் கட் ஆகிடும் இல்லையா?
எது?
ஐடி, புது ஐடி கொடுக்கணும்.
இல்லை, அது அப்படியே தான் வருது. இப்போ ஆக்சுவலாக ரெஸ்யூம் ஆகும்போது சேம் ஐடி தான் வருது. ஆக்சுவலாக சேம் தான் போயிட்டு இருக்கு.
சரி, ஓகே. இப்போ எரேஸ் பண்ணிக்கலாமா இதை?
அதில் கொஞ்சம் ஏற்றி இதுலையும் செக் பண்ணு.
என்னாச்சு? என்னாச்சு?
இருக்கா? நவீன் தானே கிளியர் பண்ணோம். இங்க இருக்கு.
கேபிள் வந்து இப்படி போட சொல்லிருக்காங்க.
இருங்க ஒரு நிமிஷம். I'll just scold them and come. நீ ஹாப்பி பர்த்டே சொன்னதால திட்டல.
நான் என்ன கத்தவே இல்ல. கேட்டிடுச்சு, அதனால தான் வந்தோம். மது நான் உனக்கு
நீ ரோட்ல இருக்கும்போதே கத்துற.
பாரதி.
அதான் நான் திட்டல இன்னைக்கு.
அதுதான் நான் வந்தேன்.
நாளைக்கு வச்சு சேர்த்து திட்டுறேன்.
மது உனக்கு வேணுமா வேணா நான் எடுத்து தருவேன். இல்ல பாரதி, கண்டிப்பா குடி.
சாப்பிடவா?
ஆமா. எல்லாருக்கும் பிடிக்கும்னு நினைக்கிறேன். காது கத்தியா? காது கத்தி. தேங்க்ஸ் சார்.
லைவ்ல ரெக்கார்ட் பண்ணிடலாமா? லைவ் அங்க வா கோம்ஸை பார்க்க சொல்லலாம்.
பார்க்க சொல்லு.
தூங்கிட்டு இருக்காயா?
சரி பார்த்து ரெக்கார்ட் பண்ணி அவங்களுக்கு போட்டு விட்டுலாம். என்ன பண்ற நீ?
போன வருஷம் முடிஞ்சு இதே மாதிரி தான் நீங்க ஒரு சௌக்க வரல. போன வருஷம்.
ஆமா.
ஓ, வெரி குட்.
Thank you so much பாரதி.
போயா கலகற.
பிடிக்கும் தானே? ரொம்ப பிடிக்கும். அதுதான் எனக்கு.
நம்ம எங்களுக்கெல்லாம் கேவலமா கேக் எல்லாம் வாங்காம கேக்கா, லஞ்சுக்கா, ஐஸ்கிரீம் கேக்கா?
தேங்க்ஸ் பாரதி. ஜெரி எடுத்துக்கோ ஜெரி. ஜெரி எனக்கு பாரதினா நீங்க ஏதோ
ஆமா.
நான் ஒரு சிம்பிளா ஒரு ட்ரீட் போட்டு ட்ரெஸ் மாதிரி இருக்கு. அந்த டப்பா எடுத்துக்கறேன். அஜய் எடுத்துக்கோ. அது ஓகே சார். ராஜேஷ் ஆன்லைன்
ப்ராஜெக்ட் நேமா ஃபைல் நேமா அது
ப்ராஜெக்ட் நேம் ப்ராஜெக்ட் நேம் தான் எங்களுக்கு எல்லாரும் கொடுத்துருக்காங்க சார். சுகில், இட் இஸ் ஃபைல் நேம் ஆர் ப்ராஜெக்ட் நேம்? ப்ராஜெக்ட் நேம்.
வாட் இஸ் ப்ராஜெக்ட் நேம்?
அவங்க பேர் வந்து ப்ராஜெக்ட் நேம்
1718 தட் இஸ்
அந்த இது
அதுதான் யூனிக் நேம் எல்லாத்துக்கும்.
அவங்க வீடியோ எடிட்டிங் வாங்கும்போது ப்ராஜெக்ட் நேம் தான் சார் போடுறாங்க.
1718 week 1 topic. It will be more easy to understand. Easier view.
Anything want to change? So he's doing 9th and 10th combined and 7th and 8th combined. Just now he confirmed.
அப்போ இங்கே 9, 10 சேர்த்துருங்க.
9th setting is 7, 8. This is okay sir or anything?
ஐஸ்கிரீம் யாரோ எடுத்துட்டாங்க.
ரெண்டாவது உனக்கு எங்க கொண்டாந்து
இல்ல பாலாஜி, அது அவரோடது.
நான் ரெண்டு போட்டோ வச்சிருக்காங்க.
ஏய் இங்க இருந்து எதுக்கு வந்து எடுக்கற?
தரல தினேஷ்
உனக்கு மட்டும் இதுக்கு 3 அவருக்கு இருக்காங்க.
அவரு என்கிட்ட கொடுத்துருவாருன்னு அர்த்தம் பாலாஜி.
பாலாஜி இருக்குன்னு சொன்னதால இனிஷியேட் பண்ணுது. அது உனக்கு ஒண்ணு இருக்கு அப்படின்னு ஒண்ணு
இல்ல பாத்தீங்கன்னா ஆக்சுவலா சமையல் அப்படிதான் வெளில வந்தேன். எல்லாருக்கும் குளிர வச்சிட்டீங்களா? குளிக்கணும். ஆமா.
டூ மச் பாரதி. இனிமேலேருந்து எல்லாரும் வந்து அடுத்தது எப்போ பாரதி பர்த்டே வரும்.
காலையிலேயே நாளைக்கு வாயில தண்ணி ஊத்தி உட்கார்ந்துட்டு இருக்கோம்.
போன வருஷம் இதே மாதிரி வருது.
ஆமா ஆமா நான் கொஞ்சம் வித்தியாசமா தான் கொடுத்துருக்கேன்.
போன வருஷம்
ஆ? சூப்பராக பண்ணிட்ட பாரதி போ.
நம்ம ஆபீஸ்ல ரெண்டு மூணு பேர் இருக்காங்க.
த்ரீ பிரிட்டி கேர்ள்ஸ் நடுவில் திருஷ்டி வரணும்ல.
ஆமா
கொடுப்பா.
பாரதி சிரிங்க பாரதி நல்லா.
நீ சிச்சதா
ஆ?
இங்க வா வெயிட்.
நவீனுக்கு வேணாமா?
அவருக்கு கோல்டு பாலாஜி, அவர்தான் என்கிட்ட கொடுத்துட்டாரு. அதுதான் நான் வந்து பாரதி விஷ் பண்ண சொன்னேன்.
இன்னைக்கு உனக்கு உடம்பு சரியில்லைன்னு சொன்னேன்.
பரவாயில்ல, இப்ப சாப்பிட்டு சரி எடுத்து போய் ஒரு மாத்திரை போட்டுப்பேன். முன்னாடி பேசி கிளாஸ்ல
அப்புறம் எப்படி சாப்பிட்ற? ஏய் வீசிங்க சாப்பிடக்கூடாதுயா. அது பிடுங்க பிடுங்க.
மாத்திரை போட்டு
அட பாவி ஒரு போதும் போ.
ஆமா
அது அட்லீஸ்ட் அதே லாவணி இருக்குது.
நம்ம
எனக்கு ரொம்ப பிடிக்குமா?
இங்கே வே. இன்னும் அப்புறமா வச்சு சாப்பிடலாமா?
நான் நல்லா தான் கிட்ட கொடுத்து வைக்கிறேன்.
அப்புறமா கொடுங்க எனக்கு. அப்புறமா நான் உருகிட போகிறது. அவங்க யாராவது திருடுவாங்க. கலை ஃப்ரீசரில் கலை வச்சுனா நீ தான்.
நம்ம குரூப்ல வரதுல பாலாஜி அந்த क्वेश्चंस
எப்படி கொடுப்பா?
நான் क्वेश्चंस எனக்கு அந்த குரூப்ல இருக்கிற क्वेश्चंस மட்டும் தனியா அப்லோட் பண்ணி
எல்லா குரூப்பில் இருக்கிற கொஸ்டினா?
இந்த குரூப்ல மட்டும்
இந்த குரூப்பில் இருக்கிற கொஸ்டின் வேணாயா? இந்த ஒரே ஒரு போஸ்டோட கொஸ்டின் மட்டும்.
இந்த ஒண்ணு மட்டும் போதுமா?
இந்த ஒரு கொஸ்டின் இல்லை, இந்த போஸ்ட்டில் வந்தது இல்லை. இந்த ஒரு நான் இப்போ எனக்கு அனுப்புங்க, இப்போ டிஸ்கஸ் பண்ணலான்னு சொன்னேன்ல. இன்னொன்று, எனக்கு நீங்கள் கொஸ்டின் எழுதுறது முக்கியம் இல்லை,
ஆன்சர் தான் முக்கியம்.
எனக்கு சால்வ் வேறு பண்ணணும். எனக்கு அந்த கொஸ்டினில் என்ன இருக்குது அப்படின்னு சொல்லி இதுக்கு வந்து இப்படின்னு சொல்லி கொடுத்துட்டீங்கன்னா நான் அதை போய் எனக்கு ரெடி பண்ணிடுவேன்.
உனக்கு என்ன வேணும்?
எழுதிடுறியா?
நான் எழுதுறேன். நான் எழுதுறேன்.
இல்லை கொஸ்டின் அவள் வந்து லெட்டர் கெட்டு இது பிரிண்ட் அவுட், இந்த கொஸ்டினுக்கு இப்படி அப்படின்னு சொல்லிடுங்க, அவ்வளோதான். டீட்டெயில் கொஸ்டின்லாம் வேணாம். போகலாமா?
சோயா
வா. என்ன பாரதி பின்ற டூ மச் போ. குட்.
கேக்லாம் தந்தா யாருக்கும் பிடிக்காது.
உன் வயசு இறங்கிடுச்சா? ஒரு பர்த்டே உனக்கு இறங்கிட்டு போகிறது ஏறுதா? என்ன வீட்டில் என்ன பண்ணுறாங்க?
நான் கொண்டாடவே மாட்டேன். இந்த மக்கள் சொல்லிட்டாங்களேன்னு தான் நான் எப்பவுமே செலிப்ரேட்டே பண்ணது இல்லையே.
சரி இன்னைக்கு ஈவினிங் ஒன்று டின்னருக்கு கூப்பிட்டு போய்
சந்திரா அனுப்புனாங்களா மெசேஜ் ஓகே சார்
நான் தான் சொன்னேன்.
ஃப்ரீயா நானே சித்ரா
அவளே கேட்டா.
ஓ அப்படியா
இன்ஃபேக்ட் நான் தூங்கிட்டு இருந்தேன்,
ஆ
மெசேஜ் அனுப்பிச்சு பாரதி பர்த்டே இன்னைக்கு.
சந்திரா தான் சொன்னாங்களா அவங்களும் ஞாபகம் வச்சுப்பாங்க என் வெட்டிங் டே ஞாபகம் வச்சுப்பாங்க சந்திராவோட அக்காவுக்கும் எனக்கும் ஒரே நாள் வெட்டிங் டே
ஸோ உன் பர்த்டேக்காக தான் நாங்கள் வந்து லைவ் ஸ்ட்ரீம் இன்னைக்கு பண்ணுறோம். வரையா? என்னத்துக்கு உட்காந்து பிடிச்சிட்டு செல்ஃபி எடுத்துட்டு இருக்க நீ? வா. இல்லை இது உங்களுக்கு கஷ்டமாக இருந்ததுன்னா அது அதர் ஆல்டர்னேட்டிவ் என்ன தெரியுமா? we can just take write it in a simple piece of white paper and stick it. ஏன்னா இதுவே ரொம்ப maybe too big. முடிக்கிட்டோம். See, you can also do இந்த மாதிரி கூட வச்சிடலாம். பிரிண்ட் அவுட்ல கையால் எழுதி வச்சிடலாம். பட் யூ கேன் ஜஸ்ட் மேக் இட் லைக் ராஜேஷ் ஸ்டாண்டர்ட் 11 ராஜேஷ் அங்கே எங்கே போட்டுருங்க. இது இவ்வளோ பெரிய போர்டாக இருக்குது, இது அப்படியே போட்டு ஜஸ்ட் ரிமூவ் ஆல் திஸ் அண்ட் ஜஸ்ட் ஃபில் இட் வித் தட். திஸ் சார்ட் இஸ் ஓகே, பட் மை சஜஷன் இஸ் அவருக்கு போடுறதுக்கு இங்கே ராஜேஷ்னு கொட்டலில் மேலே போட்டு விட்ருங்க. இல்லை அது பண்ணலாம், பட் உங்களுக்கு இது தடியாக வருது இல்லை. நான் என்ன சொன்னேன், ஒரு A4 பேப்பரில் எழுதி விட்ருங்கன்னு. ஸோ நிறையா ராஜேஷ் இது வந்துடும். எனக்கு ஆக்சுவலாக ரொம்ப பண்ண வேணாம். எனக்கு என்ன பண்ணுங்கள், நீங்கள் இதை ரெடி பண்ணி என்னோடய ரூமில் கொடுத்துருங்க. எனக்கு பேப்பராக கொடுத்துருங்க ஃபைன். ஓகே, ஏன்னா இது கொஞ்சம் அதிகமாக வந்துச்சுன்னா அவருக்கு டென்ஷன் ஆகிடும். ஸோ ராஜேஷ் மட்டும் போட்டிருக்கோம், உங்களுக்கு மட்டும் ஸ்பெஷல்னு சொல்லிவிடுங்க, அவ்வளோதான். ஆக்சுவலாக எனக்கு பண்ணவே வேணாம், அவருக்கு மட்டும். எல்லாருக்கும் போடல, ஒன்லி ராஜேஷ் சார் உங்களுக்கு ஸ்பெஷலாக இதை ட்ராக் பண்ணி பண்ண சொல்லுவோம்னு சொல்லிடுங்க. ஸோ தட் இஸ் சம்திங் ஸ்பெஷல்லி டன் ஃபார் ஹிம். ஸோ வில் பி வெரி ஹாப்பி. ஓகே பாரதி, ஏன் இண்டியா ஆஃபீஸ் போறியா? போறியா? ஏன் அங்கேயும் போய் எல்லாரும் கொடுத்து பாரதி, ஐ மீன் சாரி நாட் பாரதி, மது யாரும் பேசக்கூடாது, வந்துருங்க எல்லாம். என்னப்பா அந்த பரவாயில்ல, ஏன் அது வரல அந்த ஆளுக்கு?
சார் அது 4th குவார்ட்டர் வந்து இன்னும் ஃபைல் பண்ணல சார், டிடிஎஸோடது. அது திருப்பி இப்போ மார்னிங் நான் மெயில் போட்டிருக்கேன் சார். ரெசிப்ட் நம்ம பண்ணிட்டோம், பே பண்ணிட்டோம் சார். ஆனால் ஃபைல் மட்டும் இன்னும் பண்ணல. நெக்ஸ்ட் வீக்கில் தான் பண்ணுவாங்களா சார்? ஆடிட்டர் ஆஃபீஸில் செக் பண்ணுறேன் சார்.
எதுக்கு
இது ரெண்டு சார், ஜெராக்ஸ் மிஷின். ஜெராக்ஸ் மிஷின் இருக்குல்ல சார் நம்மளோட.
40,000
40,000
7,000
இது வந்து ஏர்டெல்லோட பில் மொபைல் நம்பர்ஸ். மொபைல்
நிறைய வந்திருக்கு.
ஆமாம் சார், ஸ்டூடெண்ட்டுக்கு மெசேஜ்லாம் அனுப்புகிறாங்க. இது வந்து ஆழ்வார்பேட்டோட இபி சார்.
இது மெசேஜுக்கு வந்து நிறையா போகிறதுக்கு they don't have a இதுவா அந்த எஸ்எம்எஸ் பேக்லாம் இருக்குமே.
இல்லை எஸ்எம்எஸ் பேக் வந்து பல்க் எஸ்எம்எஸ் வந்து ஒன் டைம் தான் சார் தராங்க அவங்க.
What does it mean?
3,000 மெசேஜஸ் 5,000 மெசேஜஸ் இந்த மாதிரி பல்க் எஸ்எம்எஸ் கொடுப்பாங்க சார். அது வந்து பேமெண்ட் 2,000 3,000 அந்த மாதிரி பே பண்ணி நம்ம
அது வாங்கிடுங்க.
இது எமர்ஜென்சியாக சடனாக தான் சார் பண்ணுறாங்க. 2 மொபைல் வச்சு யூஸ் பண்ணுறாங்க சார்.
அது புரியுது, பட் அவங்களுக்கு ஒரு பேக் போட்டு விட்டிங்கன்னா 3,000 4,000 அனுப்பலாம்ல அவங்க. இல்லை எப்போ ஒன்று அனுப்பிச்சிக்கலாம்ல.
இல்லை அது ஒன் டைம் தான் சார். இப்போ இன்னைக்கு ஈவினிங்
இல்லைப்பா, எஸ்எம்எஸ் பேக்குன்னு சொல்லி 100 SMS 1000 SMS.
இல்லை சார், நீங்கள் இவங்க நெட்வொர்க் ப்ரொவைடர்ட்டே சொல்கிறீங்களா? இல்லை இவங்ககிட்ட அந்த மாதிரி கிடையாது சார். 1000 per day 100 SMS தானே சார், பேக் கிடையாது. அது வச்சு மந்த்லி வந்து 3,000
பூஸ்டர் பேக்லாம் வச்சுருப்பாங்க.
ஆமாம் சார், அது இல்லை இப்போ எல்லாமே கேன்சல் பண்ணுறாங்க. பர் டே வந்து 100 SMS தான் சென்ட் பண்ண முடியும்னு சொல்கிறாங்க. மாதிரி பேக்கேஜ் இல்லை
See, okay. Because then you should look at our app. ஆப்பில் அனுப்பிச்சிட்டு போலாமா? மது எங்கப்பா போயிட்டா? என்னாச்சு? Moves like that. What if it moves like this? And what if it moves like that? Anantar has moved by r theta by 2. நான் என்கிட்டே பேசிக்கிறேன். இப்படி வச்சு இப்படிலாம் பண்ணேன்னா அவர் வந்து இதோ அவர் அடிக்க போகிறேன்னு இல்லை இல்லை இது அதுக்கு இல்லை. இது லென்த் ஆர் மூவ்ஸ் பை ஆர் பை 2 இதெல்லாம் வருமா?
வரும் நீங்க அதை யூஸ் பண்றதை விட இது பண்ணுங்க.
அது
உங்களுக்கு வெயிட்டா இருக்கும்ல.
வெயிட்டுக்காக இல்லை.
போர்ட்ல தெரியாது பாலாஜி.
இது இது
உங்களுக்கு கலர் இது கொடுக்கட்டுமா? இதுல கலர் ஷேப்ஸ் ஓடுது இருக்கு.
என்னது?
இதுல
இதை பண்ணுறேன். இது தெரியாதா?
வித்யார்த்தி நம்ம ஸ்டூடெண்ட் தானே.
ஆமாமா.
ஏன் என்னது?
என்ன சார் அவர் லைவ் பப்ளிக்ல போட்டுருந்தாரு இப்போ. சோ அவர் வந்து சார் என்னது இது அப்படிங்கற மாதிரி கேட்டிருக்காரு.
பப்ளிக்ல கூட தாங்க பண்ண முடியும்.
இல்லை வாட் இஸ் திஸ் நாட் yet started, is going to start ன்னு சொல்லி சும்மா ட்ரையல்
சொல்லிட்டோம். இட்ஸ் சாம்பிள் டெஸ்டிங்.
என்னது இப்போ ஃபுல் வீடியோ வந்துச்சா?
ஆமா.
Just Vidyarthi sending, "Sai sir, what is about, like, what is this about, sir?"
நோ திஸ் இஸ் ஜஸ்ட் அ ட்ரையல்னு போட்டு அதை delete பண்ணி விட்ருங்க. சரி போகலாமா?
ஒரு நிமிஷம். அதுதான் சொன்னேன். இந்த ஆங்கிள் இல்லை. கொஞ்சம் ஒரு வியூ ஹைட் இன்க்ரீஸ் பண்ணு.
என்ன பண்ணுறீங்க? why are you increasing the height?
சார் லோ ஆங்கிள் வர டைம்ல அந்த ரிஃப்ளெக்ஷன் அது தெரியும்.
சரி
சேம் லெவல்.
சரி சரி கம் let's start.
So for now lecture 2.
No, not lecture 2. இது 10 லெக்சர் பண்ணிட்டோமே.
இது I mean I'm saying for today. இது லாஸ்ட் வீக்கோட கண்டினியூவேஷன் தான் பாலாஜி.
இது ஒரே ஷீட்டு.
So it is going to be lecture 2.
3 or 4
Continuous class distribution is 1 and this is
லெக்சர் 3 அது.
இப்போ பண்ண போறது lecture.
நடுவில் கண்டினியூஸ் சார்ஜ் அப்புறம் ஒரே ஒரு ஷீட் தானா? ஒரே ஒரு ஒர்க் ஷீட்டா? ஒரே ஒரு லெக்சர் அது.
அது ஒரே ஒரு லெக்சர்.
சரி வா ஆரம்பிக்கலாம் சார். ஆரம்பிக்கலாம். டைம் ஆயிடுச்சு. நான் கிளம்பணும் அப்புறம். எங்கேயும் கிளம்பல. சாப்பிட கிளம்பணும். 2 o'clock. ஆர்எஸ் பாலாஜி வில் கம். அவன் ரொம்ப பேசினானா மண்டியில் தட்டு பின்னால் இது
பேச
வச்சுக்கோ.
மாட்டான் பேச மாட்டான்.
இப்படி வச்சுக்கோ பின்னால். டாங்.
கமெண்ட் பண்றேன். சார் தமிழ் பேசுவாங்க.
erase this please. என்னது இது? இப்போ இன்னும் லைவாக போயிட்டு இருக்கா? ஹே கைஸ் திஸ் இஸ் ஜஸ்ட் அ ட்ரையல் ப்ளீஸ் கோ. இட் வில் ஸ்டார்ட் அட் 2ன்னு போடுங்க.
நீங்க அங்க போய் சொன்னதா தெரியும்.
அது வந்துரும்.
நீங்க இங்க வந்து சொல்லிடுங்க இட்ஸ் ஜஸ்ட் a trial. நான்
Hey guys, no watching now. It's okay. It's all a trial. Okay. Anyway, I'm doing the other recording for the other class. Okay. Shall we go for area?
Ready? Action.
Okay. So let us look at how area is actually produced. Okay. How lines are produced. If I have a dot, a point, what is its dimension? Well, what dimension does it have? It has nothing. No dimension. Just one second. I'm going to redo this video. Sorry, let us restart. Ready?
Ready? Start.
So now let us look at areas, volumes, lines. Okay. If I start with a dot, it has no dimension. Okay. But if I took this dot and I stretched it out, I am adding a new dimension. This starts with 0 dimension, right? But if I start with, let us say, a dot and I pull it out, I'm going to get a length, right? Well, if I pull it out like this, I'm still going to get a length. It doesn't matter, but I'm always pulling it in some sense perpendicular to that 0 dimension. But with 0 dimension, you don't have to worry, because however I pull, it is perpendicular to the original dimension. Okay, so when you pull a dot out and stretch it out, you produce a new dimension. We call it length. Okay, now suppose I already have a length. So let us take this example of a rod. Okay, so I have already pulled it out and created a dimension. Now if I took this rod and I moved this rod down, okay, so that means I have a rod originally, and this rod is moving down by, let us say, some amount of distance. So let us call that B, let us call this L. Okay, so what did it produce? It produces an area. Okay, so we call this area length into breadth. Okay, now the point is, this movement has to be perpendicular to itself, to this rod. Now you may wonder, how will that be possible with a length like that? But we will see. We will be able to do those things as well. But first try and understand this. If it moves perpendicular to itself, then it produces an area. What if I take this area and I move it like this perpendicular to itself? It will produce a volume. So if I start with an area like that, so imagine that this was a flat area like that. Okay, it doesn't matter that this area was a circle or a square or a rectangle. If I just decide to move this like this, or I'm going to say this is a flat area like this that I'm lifting it up. So if I decide to lift it up, what will I get? I am going to get a cylindrical shape. Okay, for every point here there is a perpendicular distance that way. So let us say that you have moved up h. So the volume that is being produced when an area moves up perpendicular to itself is A times h. Please keep in mind that all of these movements are perpendicular to itself. Now what is interesting here is to ask the question, what if this line did not move perpendicular to itself but decided to move parallel to itself? It will produce 0 area, because if this fellow starts to move like that, actually it has not produced any area. It's just simply, it used to be here, now it has moved there. You can see that first of all it has not produced any area, it has not swept any area. We usually call this sweeping of an area. Just imagine, think of this as a broom, so it is actually sweeping an area. We think of this as sweeping. An area is basically sweeping out a volume. Okay, whereas when it is doing this, it is not sweeping out an area. So if this object moves like this by, let us say, dx, it produces an area L dx. But if this fellow decides to move like that dx, it produces an area which is 0. Please keep that in mind. Now the question is, what if this fellow decides to neither do that nor do this, but it goes like this? Well, you know that it's going to create a parallelogram, because it moved parallel to itself, which basically is not perpendicular, okay, but it kept moving that way. So it moved this way. Let us say this was breadth. But it is not going to produce an area which is L into B, because the only thing that contributes is the perpendicular movement. It moved perpendicularly h. So therefore the area of the parallelogram is not L into B, it is still L into h. So you can think of it as, first of all, creating a rectangle and then shifting everything this way. This movement does not produce area, only this movement produces area. I hope everybody is clear about that. The same way, if I had an area and that area decides to move this way, that is, you are taking this area and instead of moving it perpendicular to itself, you are moving it like that in a slanting way, it does not produce A into the slanting height or the slanting length. It doesn't produce that much area, volume. It will produce a volume which is A into h, not A into L. Okay. In all of these cases, it was simple. Basic idea is a length moving perpendicular to itself produces an area. Okay. And we are interested in small areas and small volumes the way they are being produced. So suppose I had an area and it moves perpendicular to itself. a small amount upwards like that, this is dH. So what is the volume? ADH. And that will be dV. Okay. Now consider a situation where I have a length which is actually a circle. And suppose you want this segment of, or this section, this, okay, not a segment, but the sector's arc, the curve arc, I want it to move perpendicular to itself. What is movement perpendicular to itself? How will it move perpendicular to itself? It will move like that. Okay. It could also move like this. That's also perpendicular, and that's very nice, because if it moves like that, it's very easy. What is it? This is going to be 2 pi r. And when this thing moves up like that by h, it will produce a surface area. Line moves perpendicular to itself, it will produce 2 pi r h as its area. And we call that the curved surface area. Okay. But now I don't want it moving perpendicular this way. I want it moving perpendicular that way, because that's also perpendicular. The only problem is when this fellow goes there and then this one goes, let us say here, there is going to be a small crack. We will assume that such a crack does not exist. So if this fellow moves perpendicular to itself, it has moved out like this, but we are hoping that this is, because there is no crack, the way there will be no crack is if I have moved a very small distance. So this cannot be done when you are actually moving out even this much. I should just say I am moving a very small distance. So let me draw it again. So here I have the circle. It has length 2 pi r and it is moving up by a very small distance. That much. Okay, so this is dr. How much is the area that it has produced? Using our logic, if a line moves out by a distance perpendicular to itself, how much will it move? It will move length into distance that it has moved perpendicular. So 2 pi r dr must be the dA. But you already know this. How do you know this? Because area of a circle is pi r square. In fact, that comes from this, by the way. Okay, so if I took d of area, okay, so this would be dA. What is d of something? It is the change in that object. So this is the change in the area. That area minus this area is actually written this way, pi r plus dr square, because that once the radius has gone from r to r plus dr, that is the new area, minus pi r square. If you calculate this, you will get pi r square cancelling out. So you will end up with 2 pi r dr plus dr whole square, which is very trivial because dr itself is small. So we will basically end up with this. But you already know, to differentiate pi r square, the differential of pi r square is pi 2r dr, exactly what we get. But you can also think of it as this length 2 pi r has moved out by a small amount dr. So length, when it moves out perpendicular to itself, and this is important because it's perpendicular to itself. If it was not perpendicular to itself, it does not allow. Okay, it has to move out perpendicular to itself. What if it doesn't move perpendicular to itself? What if I had a length which actually moved this way, which was not perpendicular? Resolve it into two components. You say there is a movement like this and there is a movement like that. Only this movement will contribute. So length into this movement will be the area produced, though actually it will turn out that the area will be in this shape. But that area and this area, you know, is the same, because that's the exact idea of the parallelogram. Okay, but in this case it moved out perpendicular to itself. The only problem is I can't use this for too long, because as soon as it moved, it will crack and it will basically break up. If you think of it as a circular ring, the ring goes out. Maybe you can stretch it out a little bit, but if you try to do it a little bit more, then the ring is going to break. So think of it as it is expanded a little bit and now it has to be a new circle. But for this limited portion, we can assume that the circle length remains constant. So it is 2 pi r dr. So that will be the extra area. Now the same logic will work when I am trying to do this for volumes. For example, if I had a sphere, right? Suppose I wanted a ball. Let's take a ball. So let us take this ball. Okay. Now suppose, imagine that this ball, what is the surface area of this ball? 4 pi r square. Now if this ball expands by a small amount, that means this area is moving perpendicular to itself. Notice the point, that is moving perpendicular to itself. Okay, but it is not moving that far away, because then by the time all the surfaces will crack. So you're moving very small amount. So if I just move a very small amount, think of it like that, then what is going to happen? This area has moved out by a dr, this area has moved out by a dr, so 4 pi r square has moved out by a dr. So therefore, the produced volume, the new volume that is getting produced when this fellow goes out like that, is 4 pi r square dr, and that must be dV. But you already know the formula for the area or for the volume is 4 by 3 pi r cube. So dV must be d of 4 by 3 pi r cube, because when r changes, how much does volume change is the question that we are talking about. So when r changes, the volume changes by this much. But you can see clearly that if I did a differential of r cube, I'll get a 3r square. The 3 and 3 will cancel out, giving us 4 pi r square dr. But you can see that we have now derived it in a different way by saying 4 pi r square dr. This is a more general way. In fact, the way you will derive the formula for the volume is exactly this. How will we derive the formula for the volume or formula for the area? Let us quickly do that, okay, before we proceed. So if I want the area of a circle, many ways of doing it. So let us take one. You say, oh, I know that this is 2 pi r, because this is r. So in fact, let me call this x. And so this will be dx. So what is the area of this tiny ring? dA is 2 pi x, because the circumference is 2 pi x, dx. But I want this whole disk's area. Okay, so let us say that was capital R. So I'm going to cut this up into small circles. Okay, so I'm going to add up that area plus this area plus this area and so on, which means I'm going to do dA1, dA2, dA3, dA4 starting from here all the way till there. Okay, so you're cutting it up into many small, tiny rings. Each ring has some thickness. How much is the thickness? dx. Okay, and what is the area of that little tiny ring? 2 pi x dx, because it's actually a very thin ring of 2 pi x circumference, just moving out dx. And then from there to there, it's a new x and a new dx. So this is the way to write one particular ring's area. So this is actually just this ring or that ring's area, some random ring's area. Now I want to add this up, and addition is actually integral. You want to add this up from when x was 0 to when x is r. On the left side, you will never worry about the limits. What is this saying? Cut it up into lots of small areas. But I have already done that, because if I wanted the whole thing, I have cut it up into this plus that. But this itself is not such a small, tiny, thin. It's a little bit longer. So let us make that thicker. Let us make this thicker. Okay. Now each one you are basically saying has thickness dx. But after this, now I must take from here to there, right? I'm not drawing it, but you must. And then from here to there, and then from there to there, and there to there, and so on. So you are cutting it up into many small rings. Each ring has this much area. And so this side simply tells you that you cut it up and add it, you will get the full area. This tells you how you have cut it up. But when you have cut it up, for each little bit, the x goes from 0 to r. And if I want to add this up, you know 2x dx is d of x square. So when you integrate, you will get pi x square from 0 to r. And so it is pi r square minus 0. And so we know the formula pi r square as the area for the disk or a circle. Right? Now if I want the same thing for volume, we use the same principle. Okay. Now obviously you know these formulas, so it is easy to think that we can do it. But as we get to more complex things, the same principle will work. Now if I want a big sphere and I want to find out what is the volume of this sphere, let us take a small surface. Okay. Now what is the radius of this surface? X. Now this fellow is going out by a small amount. So we will say that that is dx. And we are going to assume that you already know the surface area formula, which is 4 pi x square. So 4 pi x square dx. Then you may ask, how do I know that is the formula? We will come to that at some later point. But at this stage, let us just say it is 4 pi x square dx. 4 pi x square is the surface area. Dx is the amount it has moved. So what is this? dV. Now if I add up all such dv's for this one, this radius, that radius, the next radius, etc., which means the radius is going from x is 0 to x is r, this will give me the total volume. Again, on this side, I don't particularly care about the limits of the dv. It is just to say add up for every bit. But what does add up for every bit mean? It means go from x is 0 to x is r. Okay, so now if I try to do this, it is 4 pi. You know that integral of x square dx is x cube by 3. And so between limits of 0 and r, so that gives us 4 by 3 pi r cube. And the reverse is d of this fellow is 4 pi x square dx. So there are many ways of going back and forth. There's only one more thing to keep in mind. So just keep this basic point in mind. How is a volume produced? The surface area moves out by a small amount, volume is produced. But it has to move perpendicular to itself. Now there are situations where you don't move. Every point in the line may not move the same way. Now for the circle, when we are cutting up this circle, notice something interesting. Whether I took the sphere or I took the circle, this was moving up by how much? Dx. What was this little portion doing? This was also moving by dx. This was also moving by dx. Everybody was moving the same amount. In fact, if I had a shape like that and everybody moved perpendicular to itself. Now that's a little weird here, because when this fellow moves perpendicular, it will be like that, and when that fellow moves, it will be like this. So let us say I have created a new surface like that, which may not have the same length, by the way. Okay, but let us say that we have created something of this sort, which we are not going to worry about. Suppose this had length L and this was dx. How much do you think will be this area? L dx. Okay, as long as everybody moves the same amount and perpendicular to itself. Now, if I took a rod and then, let us take this rod as an example, and then what I do is I move this rod like this. Now what has happened is that I am turning the rod. Now the problem is that this point has moved perpendicular to itself. You know that the velocity is going to be perpendicular to itself. This was also moved perpendicular to itself. This has also moved perpendicular to itself. But they have all not moved the same amount perpendicular to itself. See, this guy has moved this much, that fellow has moved that much. And this poor fellow has not moved at all. So if I call this length r, this guy has moved much more than this fellow. How much has this guy moved? Well, if I call this angle theta, you know this fellow has moved r theta. And what about this guy? Has moved 0. And basically the average, if you think of overall, r length into the average distance they have moved, r theta plus 0 by 2, r theta by 2. Now that should be the area produced. So what is the area of this sector? Half r square theta. If I decided to go now a full circle, notice that this rod has moved like that, right? This rod has actually moved all the way around. This point has not moved at all, but that point has moved full circle. How much is that? 2 pi r. But this guy has moved 0. So average movement is pi r into r. Because how much you have moved perpendicular, and has it been perpendicular? Yes, at every time, every instant it has been perpendicular. When you come here, this is moving perpendicular, this point is moving perpendicular, that point is moving perpendicular. The problem is not the perpendicular. The problem is that how much are they moving? They are not moving equally. So obviously it rotates, and so then you say average. So average movement is pi r. So this is pi r square. Okay. Now the same issue will land up when you have a circle, a sphere. So if I took a ball, then you have to then think, it becomes a lot more complicated. Okay, because then you cannot so easily say that the average is like this. Okay, but we can use it in cases where it's a straight line motion. When all of them are moving, like look at this, suppose this rod rotates, this does not move, this moves that much. Your velocity profile is going to look like this. The closer you are, the slower you are. But if you look at overall how they have moved, it is distributed linearly. But it is possible that as it's rotating, it may be like a belt instead of a rod rotating. If suppose I had a belt rotating, then the belt could basically even turn around as it's rotating, no? In that case, you cannot just say how much that has moved plus how much it has moved divided by 2. No, that won't work. Okay, let us take two other examples. Suppose I had one object like that. Instead of coming down, what is happening is this guy goes this way. As long as it was a small length, I can just happily say, well, this has come down, and so this is dx. I can say that this area is L dx. Okay, but wait a minute, what about this little extra and that little extra? Even compared to that L dx, those tiny things are so small that we'll ignore them. But we'll ignore them only because they are really small. If, on the other hand, it was like this. Now you can't say I'll just ignore this, right? You can't say this area is equal to that area. Suppose this was L1 and this was L2. L or L1 or L2 have moved a distance h. But the point is it was neither L1 moving h nor was it L2 moving h. So we are going to assume that it will be L1 plus L2 by 2 into h. You already know that for a trapezium, you can say it is a plus b by 2 into h. Now this assumption is valid because we are making the assumption that what is moving from top to bottom is an average quantity L1 plus L2. It is okay because it's a straight line. Do you think if it was moving in such a way like this, it will still be L1 plus L2 by 2 into h? No, right? Because obviously this is not. Suppose imagine the situation where this came down almost like that and bent. Clearly this area is not going to be the same as the trapezium area. Or if it was like this, that area is going to be bigger than the trapezium area. So it is not easy to then conclude what to do. But how do we calculate these quantities? How do we do it? Very straightforward approach. What you do is at a particular height h, you find out what is the length. In this case, it is all nice because once I take a particular h, the length is going to basically be proportional to the height in some sense. It will be, if I am starting with, like let's say in this particular case, it will be L2 minus some whatever that, some k times h. Okay, or L1 plus some k dash times h, if you start from here. Okay, so you will find that you can do one of the two. You can say as I am going down this way, my length is increasing. It is increasing. The increase depends on h because this will be proportional to h. It will depend on the slope. Both of them may not have the same slope. You will need to do a little bit of working around it. But the basic idea is it will look like this. But in this case, I might need to know what the shape of this curve is. But anything, anyway, this is going to give me some formula for L, which will depend on h, right? So therefore, at this point, if this L goes up by a small amount, and how much does it go up by? dh. How much area will it produce? dA, which is L dh. That will be this area. Why? Because this length has moved up by h. Did it move up perpendicular? Yes. And was it moving all of them equally? Yes, because well, it was an expansion of the length. As I kept going down, this length became a little shorter, but it was not like this moved a different amount and that moved a different amount. So yes, this will be the area. Then you can do an integral and find the area. In fact, this will be a way to usually find the area of a weird shape like this. Of course, if it moved in such a way that it was a straight line, we will keep in mind that if it's moving, increasing linearly, then we can just simply do the average between the two, but only for linear. It's exactly the same idea as what you do for uniform accelerated motion. You can say initial plus final by 2 is the average velocity. You can't say that for everything else because the velocity increases uniformly. If the length increases uniformly, which means a straight line, you can say this. Because as I'm turning around, the velocities increase or the displacement increases linearly with this distance, then I can say average is 0 plus r theta by 2. So r theta by 2 into r. So is that hopefully clear? Now what will happen in a case where I have something that moves like this? So let us draw it. Okay, think of it like this. So this is also moving, that is also moving, except it's turning around like that. So you may end up with something that looks like this. Then what happens? Now assuming that this is also perpendicular and that's also perpendicular, so they are going to cover a circle, but they have not yet done that. You will end up with a theta and you will have an L. Okay, so if I did R1, how much should this be? R1 theta. How much should that be if I call that R2? R2 theta. How much do they move on an average? R1 plus R2 by 2 theta into L, which is how much? R2 minus R1. Right? So if you look at this, you will end up with R2 square theta by 2 minus R1 square theta by 2, which is saying that this area minus this area. But you have actually got it by saying average of these two into L. Keep in mind that this guy is moving perpendicular. If this fellow decides to move like this and turn, then it won't be true, because then it is moving like this. Okay, and it's also turning. So then your area becomes a little more messy. You will have to look at situations where you can convert it and do. So I hope this basic idea is simple. Okay, you understand how to take it when you are trying to find the volume produced or the area produced because a line moves like this or line moves like this. It's important to do that. Why are we doing all this? Because it will turn out when I want to calculate charges. Okay, usually I am going to end up saying charge now depends on radius, which then means where is the charge constant? Remember, our whole point was find all the places where sigma is constant. Your dA should be such that sigma is constant. Well, if it turns out my sigma was constant for this region, then I want this area, because for this whole area sigma is constant. Do you know how to find that area? Yes, 2 pi r dr. And then that area has sigma constant, so which means I can find dq for this area, which will be sigma times dA. But do you know the dA? Yes, how much is it? 2 pi r dr. Now can I find from this charge, can I integrate and find the entire thing? Yes, because you can do that. Or using this charge, can you find at this place a potential? Now that depends, because that may not, the potential may not be the same for this point and that point and that point, even though sigma is constant. Then you'll have to worry a little bit more and do some extra work. But for finding charge, it's very simple. If sigma is constant, you can just simply write this. On this side, you don't have to worry about the limits. On that side, you will need to worry about the limits. So I hope this is clear. Simple idea. Point moves, produces line. Line moves, produces surface. Surface moves, produces volume. For example, how do I know? Let's think about, I told you that we used 4 pi r square, right? Let us see now whether we can produce 4 pi r square without using the formula. Okay. How do I know that this surface area is 4 pi r square? Can you figure out a way, something producing this surface? You can think of an arc like this or a circle like that. Now imagine that the circle is rotating. Will it produce a surface area? So think of a circle. Now this is a circle. How much is this? 2 pi r. Now this circle has to rotate like that. Well, if it does 1/2 rotation, that's good enough. Because if this guy does a half rotation, this would have gone the back side. So this is doing a half rotation. Okay, this is a 3-dimensional case, so I can't show it. So what I want you to understand is, there is a circle here, and that circle is turning around like that, like a ring. So that is the amount it has moved. Now has every point moved the same amount? Yes. No. Think about that. This fellow has not moved much. This fellow has moved that much. This fellow has moved that much. That fellow has moved that much. The last dot that was there in that ring has actually not moved at all. Think of it as a ring that is being rotated. This last dot has not moved at all. So how much is the motion of this point? 0. How much is the motion of that point?
Maximum.
So it has gone from here to there? Okay. So can I call that something? How much has it moved? Well, it has gone on full circle. I should call it pi times r, because if it went all the way around, it would have been 2 pi r. Okay. Now this thing should be some average of the two. Unfortunately, I cannot do pi r plus 0 divided by 2. This one turns out to be 3.14 r. This fellow has moved 0. This fellow has moved a different distance. That has moved a different distance. But it has not all moved proportional. Like if I keep going closer and closer, I cannot say it is moving proportionally right? Therefore, I cannot do half of this. Okay. It will turn out that this fellow's average will turn out to be 2R. Okay, we not proved it, but it will turn out to be 2R. It has to be less than 3.14, that is clear, because that guy has moved 3.14 R. This guy has moved 0. Okay, so the average will be 2R, but the average is not equal to half because it is not linearly increasing. Because look at the shape at which this is. So these fellows will move a lot and this guy will move, it's not like this. On the other hand, if I had a nice shape that way and it moved, then it would have been simple because it would just depend on the distance. Whereas the curve is like that. So we'll have to do the average. It turns out the average is 2R. If it moves on an average 2R and there are 2 pi r, the length is 2 pi r, you will end up with 4 pi r square. Of course, this is not proof because I have not shown that this is 2R. How will I find surface areas? So let us now think about that.
Cut.
See, இப்போ என்ன பண்ணுறோம், நான் கிளாஸில் ஒன்று என்ன பண்ணேன் பாரு, இது வரைக்கும் ஓகே வந்ததா?
இது வரைக்கும் ஓகே பண்ணுச்சு. அந்த 2R-க்கான ப்ரூஃப் தான் இல்லை இல்லையா?
ப்ரூஃப் 2R-க்கு ப்ரூஃப் இல்லை. நான் இப்போ ப்ரூவ் பண்ண போகிறேன். ஸோ இங்கே 2 சர்ஃபேசஸ் இதெல்லாம் பண்ணிட்டேன். Okay, can you hear? Okay?
Rolling action.
Okay, so this is an instruction for Madhu and the editing team. So, okay, so basically this is to be added as part of the varying charge, the end segment, okay? And then after that immediately we'll do an exercise, then we will go to charge. Lastly, I might have finished at the varying part saying that we are going to look at area. So, I'm going to redo that part. So, okay, you can cut it off before that area. Okay, shall we start? Okay. So, let us look at a few steps for integration. Okay. After that, we will look at questions which involve just simple line charge. Then we will look at understanding how to do things for area. But the same principles of integration will still work. So, what do? There are basically 4 steps. So, let me write these steps down when you are trying to solve a problem. The third step is where you are trying to find dq. So, I am going to write dq. You want to find the charge dq. What is that going to be? Lambda dl, or it is going to be sigma dA, etc. So, this is going to be lambda dl. Now, lots of people are in a hurry to put an integral symbol on top. Focus on the dq. Don't worry about the integral symbol. Okay. So, after you do this, the third step will involve putting the integral symbol and then figuring out the limits. Okay, but this is the third step. To do this, the reason I wrote the third step is because the third step will define your first and second step. To write something like dq is lambda dl, you are talking about where is dq lambda dl. So, you first have to talk about location. Okay. Now, you can always say I have an xyz coordinate and location is x comma y comma z. But the clever way of doing this is to do this in such a way that lambda is constant for the dl. If it turns out to be constant on an arc, maybe you should choose your location in such a way that you can nicely get an arc. Suppose it turns out that lambda was constant for rings. Using xy system is not great. But using an r theta way of coordinate system is good, because for each r, lambda will be constant. Like if I had lots of rings, okay, and I wanted to look at lambda for a ring, using r as the defining coordinate system, your location becomes a little easier. So, location depends on the particular problem. So, this could be the coordinate system. It is also defining variables. What is x? What is r? What is theta? Okay, defining all of those variables is part of the first step, location. When we do problems, you'll understand what that means. The second is to first figure out your element. Element length. Okay, so this is dl or dA area, and element volume, which is dV. Right? Now, what is dA? What is dV? Now, dA is not always very straightforward, because, so let us take the example of a circle. And if I want to find, basically I want to cut it up this way, the dA I may want is this dA. And it won't be in terms of A, it will be in terms of X. Okay, now in terms of X I want to write this dA, and that's a job to be done. It is not, I'm not saying it's difficult, it will turn out to be 2 pi x dx like we will see, but the main point is to write the dA. That is an important step. In fact, some people call dq itself as an element. That's a good way to think about it, and we will do that for when we get to potential. Potential, what will happen is third step will go and join the second step, or we will actually insert a separate step. So, we'll, instead of making it 4 steps, we'll make it 5 steps. Okay, but for us right now, we are talking about an element which is dl or dA or dV, and then using this element, for that element you are finding dq. If you want to finish the problem at this stage, that means you are trying to find charge, you just simply add this up and find out limits. Now, remember, if you just want to find area, you will stop here. You don't need to find q. You will just simply add up the dLs or dAs or dV. Whereas if you want to find charge, you will first find dq and then add the dqs up. But if you want to find potential, you don't stop there. You will do dV, which will depend on dq. And then you will use dV and add up dVs for all the dqs. but all the DQs will mean all the DLs or DAs. Okay, so right now I'll just write lambda DL. It may be sigma DA or rho DV. Okay, but don't focus on the integral, focus on the DQ. Okay, then, and you should be able to explain what this means. You have to say, this is the charge on this ring, or it may turn out that this is the charge on this square. Okay, or this may be the charge on this thin piece like this for some reason. You may want to take that as your dA. Okay, now you have to be able to define and say that dq is this much, this is the charge on that particular element. That element has to be defined there. Then comes the actual integration calculation. Integrate and calculate. People jump to this step without focusing enough on this step or those two steps. Now remember, the third step is critical, because the third step, because it's going to say lambda DL, is only true when lambda is constant. So you have to, or sigma DA is only possible when sigma is constant. So you have to cut this whole thing up in such a way that the sigma is constant. Now to cut it up means you have to, that is your job here. So the location is not an independent question, it depends on the particular question. Based on that, you will end up with elements, or actually to do this you will need to the element. That element must be such that the sigma is constant for it. Therefore, you will choose your location such that will give you that element. Okay, so all of these steps are connected, and so these 4 steps together will be the key steps to find charge. So these are integration steps for finding charge. If you wanted only to find area, you will skip step 3. You will find the element and use it as add. Then you are not particularly interested in where is the charge constant, because, well, it doesn't matter, there is no charge. Okay, but for us charge is important, so we are going to cut it up in such a way that the charge density, lambda, sigma, rho, is constant for that little element that you have chosen. Okay, the whole point we are choosing and doing integration is because lambda is varying. Right? Now, if you choose your element itself in such a way it's still varying, it's not useful. So for example, you may end up with things where it may be a function of x and y. Now if I decide I'll cut it up like this, but it's going to change, y is going to change. So that means your sigma is going to change from point to point. Well, if sigma changes from point to point, I cannot say sigma into this dA. This is not correct, because sigma is varying. Then I need to figure out a little sigma, little dA, maybe something like that, for which it is constant. Okay. On the other hand, if it did not depend on y, it only depends on x. That means for this particular value of x, all of these have the same value. Then you can do this because it's simpler. Suppose it only depends on y, sigma was a function of y but not of x, then it's a good idea to take this fellow. So which one will you take depends on the lambda or sigma or rho, and then, but then you have to go back to location, then you have to look at element, then you have to look at dq, and then finally put the integral symbol, find limits and integrate. So is the idea clear to you?
Cut.
ಇದು ಎவ்வளೋ ಟೈಮ್ ಬಂದಿದೆ? நடுவில் தெரிலன்னா எனக்கு ஜஸ்ட் ஆமாம்
எனக்கு வரவே ரோடே
இது இங்கேயே பாரு
இல்லைடா half an hour நான் ட்ரை பண்ணுவேன் சுற்றிட்டே இருக்கேன் வரவே மாட்டேன்
அது ஒன்று போட்டால் தானே இப்போ 215 to 215 தான் போட முடியும் இதோ பாரு
சார் ஏற்கனவே ஓடிட்டு இருக்கு எனக்கு வீடியோ நான் நடந்து வந்தது நான் பார்க்க முடியல யூடியூப்ல
இல்லை இல்லை அதோ போயிட்டுருக்கு இதோ
இது நான் போட்டேன் எனக்கு ஸ்லோவாக
இப்படி வை வருதா இப்போ அது 8 seconds லேக் இருக்கும் வரல ஆன் ஆயிடுச்சா லைவ்ல தான் இருக்கா என்ன சார் வரலையே இல்லை இல்லை
வைஃபை நம்ம உள்ள வைஃபை
இதோ வந்துடுச்சே
வைஃபை உள்ள கம்மியா இருக்கு
சரி கொண்டா 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 ஃபர்ஸ்ட் இதை ஆஃப் பண்ணிட்டு இருமா
Coming up there, Baji.
சரி வா ஷால் வி ஸ்டார்ட் ஆஃப்
Yeah, yeah.
ஓகே ஓகே கைஸ்
ஒன் சாலட்
அது உட்காண்ட்றியா So it's on, right? Ready? Sound போட்டிங்களாப்பா சுகில் sounding sound is okay sound is okay you have your phone, right? So I don't need this. Okay, I'll just keep it somewhere.
லவுடாவே கேக்குற மாதிரி இருக்குங்க
கீழே போட்டு அங்கே உடச்சிடாத Okay, so shall we start off? Okay, so welcome to the first live online session, okay, with AhaGuru. Okay, so you had a couple of questions that you sent out. Okay, so I just saw it. So I'm just going to explain one important and useful idea. Okay, then we will try to do some of the problems. Like for example, one question that some of you guys have asked is if there are two discs connected by a spring and basically you give this a push, what will be the velocity, etc. Now these kinds of questions land up many times, so it's useful to learn how to address some of these questions in general. So there is a very simple principle involved, which is there is a connection between momentum and angular momentum. That's it. So for example, let's take this idea. If I had a disk which was, let us say, rotating with omega in the beginning, omega naught, and it was rotating like that, and I dropped it on a floor. So what is going to happen as soon as it hits the floor? There is a lot of friction. It's a rough surface. Okay, so generally with rough surfaces, when it suddenly drops, you don't have much time, you're going to definitely lose energy. But if I try to look at a situation where if something is rotating like this, and it comes and hits this place, what is going to happen is that the bottom is going to move this way. So it's going to try and slide that way. So there's going to be friction this way. And the friction does two things. So let us place this fellow down. So after it has hit the ground, or like just been placed on the ground, this point is moving like that. Suppose I call this radius r. Okay, so r omega naught is your velocity in the beginning. Actually what you're going to get therefore is that this floor is going to exert a force F, which may change, may not change. Right now we don't even care. It's a friction force F. At this point there is no other force acting on it. So this F will produce a change in momentum in that direction. And so we can write F into T is m, suppose I call its mass m into final velocity minus m into initial velocity. Right now initial velocity is 0, but I'm going to continue to assume that there was an initial velocity. So V initial. Okay, because it need not have been this particular problem. This is a general approach, right? So instead of worrying about this problem, imagine that I threw it like this. So instead of dropping it, all I have to do is to take this basket, whatever this, well, what ball is this? Volleyball. If I rotate it and throw it, when it hits the ground, it's going to move with a horizontal velocity and a rotation, right? So you will get both. So let us say mvf minus mvi. Now if I take this, this is an equation which involves f. The problem is we don't know what is f. Now let us look at another equation, which is F into R is the torque in this direction. So if I look at Fr, torque into time must be the change in angular momentum. Okay. Now the angular momentum has to basically change in this direction. So finally when it starts to, let us say, roll, it has a velocity Vf. At this point its velocity is Vi, which is 0 for now, but we'll just take it as Vf there. Now if I look at this Vf, when you're rolling, your omega must be in this direction, but that is going to be omega f. Okay, and instead of calling it omega naught, I'm just going to call it omega I, just for consistency. Now I have to be very careful because Vf and Vi and omega I are not related as Vi equals R omega I. That is, so maybe I should go back to calling it omega naught. Okay, so but when I finally have an angular velocity omega f, there is a relationship for rolling, which is the velocity here must be equal to the velocity there, but that is 0, so this is 0. So R omega f plus Vf, R omega f is in this direction plus Vf in that direction must be 0, or, well, if I don't use the minus sign, R omega f magnitude must be the same as Vf magnitude. Right? So this basically is an equation finally. But let us think about the angular momentum at the end. What is the angular momentum? mr square by 2I into omega f minus mr square by 2 into omega initial. Okay. So I'm going to write it like this. So that gives you something to do with the change in angular momentum. Okay. Somebody's talking. Just go there. Okay. So let us get rid of this R. You can see that this is equal to that. I don't know what is F, I don't know what is T, but I can definitely connect M into delta V is mr by 2 into delta omega. So this tells you change in linear momentum, that tells you change in angular momentum. Okay, so or we can rewrite this as delta linear momentum, usually we use the symbol P for it, right, times R is equal to delta angular momentum, because angular momentum change is basically mr square by 2 I omega. So there is a change in angular momentum, there is a change in linear momentum. So you get a direct connection between linear and angular momentum. Okay, so now this was with a simple case where something is falling down, or just you place this and so you worry about what is going to happen to it. Let us actually solve this problem, then we will worry about the next problem. So let us look at this particular question. I'm going to just straight away use this equation. Okay, so I won't use this ft and so on. And initial velocity is 0. So all I have to do then is to simply say, so you can write the ft and solve it, or you can directly say that m into final velocity must be equal to mr by 2 into omega final minus omega initial. But omega v final is r omega final. And so that gives us 2 omega final is that. So omega final, 2 omega minus omega final is minus omega naught. Is that correct or wrong? This is not correct, no? This is not correct. Let's see what went wrong. Let's see, this is not correct, because I didn't leave the 2. Did I miss out a minus sign is all I'm thinking about. Sorry. I missed a minus sign. So I was wondering something is wrong somewhere. So it is this. There's a minus sign. Okay, because F into T into R is in this direction. Okay, so I should basically assume that that was minus FTR. So when I wrote it, FT is M delta V, but FTR is not M delta V because FTR is in the opposite direction. So we are assuming omega to be this direction. So it is delta omega into I, but it is minus sign. Okay, so if I now cancel out and bring this R down, you can see that this plus this is 0 actually. So R times delta P plus delta L is 0. Magnitudes are equal, but they are of opposite sign. So here I should put this as minus sign. We put a minus sign. So then you will end up with 3 omega F is omega naught. Omega F is omega naught by 3. Okay, but this idea that linear momentum change and angular momentum change are related is a very useful one. So we can directly use it for many types of questions. So this is one of them. Let us try applying it to this question that you asked. Okay, except when I'm doing it for that question, I'm going to do it by starting off with this as a principle. But here if you think about it, there are many different forces to worry about, right? There is a spring force. So if you think there is a force here, there is a spring force here. So what is the question? Let us repeat the question. Is this visible or like you want to clean it up? Clear or clear? This thing is just quick clean minuting. Yeah. Let's read this question. Okay, so let us try this question. Now, in this question, what was the idea? There are two disks of each of radius r, mass m. Both are the same mass, right? And there is a spring constant k, there is a spring connecting them, and they are on a rough floor, and there is no slipping, I am assuming. And this center of this fellow is given a velocity of how much? V naught. Okay. What is the maximum compression and
Velocity of center of mass when
velocity of
maximum
center of each of them? Basically, both of them will have the same velocity at the center of mass. Okay. Now let us think about this question. Think of this simple idea. If there is definitely, this fellow is going to slip this way, so there is definitely going to be friction like this. But the friction will keep changing. It's friction as a function of time. But there is also going to be a spring force, because as you start going that way, there is going to be a spring force this way. But there's going to be an equivalent spring force that way. And that is true because the spring is massless. What if the spring had mass? The two ends won't have the same force, because you'll need a, if you want to. But that's, I'm saying right now it's massless, so this is kx, that is kx. Now there is a friction force here. This will get pushed that way, right? So this will start to, like you can either think of it as at this point, the friction force may be that way, maybe this way. So let me assume that the friction force is like this, but it will be a different friction force, F1. Correct? Now this force and this force will produce a change in momentum. So I will write it like this, Kx and F will contribute to M delta V into T. It's not a plus, it's an and. I have to figure out whether it's a plus or minus. At this point I don't care. Okay, now Kx and F1 into T will contribute to an M delta V for that fellow. Okay, so I'll call this V1, I'll call this V2. It doesn't matter. I'm not writing plus, I'm just saying and. Okay, so basically I'm not even trying to write the equation. I'm saying this will contribute to a change in momentum. These two fellows will contribute to change in momentum of this one. So all forces together will contribute to change in momentum of this system. Now, this kx and that kx, the momentum contributions will cancel. Right? So I can actually say, if I add this whole thing up, F and F1 t will contribute to m delta V1 plus m delta V2. Change in momentum of the entire system. Now, F will contribute to a torque about the center. So F T R will contribute to change in angular momentum 1 about the center. Kx won't contribute to it because Kx is acting at the center. This Kx also does not contribute. Similarly, F1 TR will contribute to delta L2. And if I add this up, this torque plus this torque into time will contribute to total delta L. But we know that if force contributes to change in momentum and torque like this contributes to change in angular momentum, there is a relationship between the two, so directly use it. So what you can do is to say R times this fellow, M1, let's put some symbols. Let us say that finally this guy has a velocity of V, this guy has also a velocity of V. Initially is V0 and 0. So final momentum is mv plus mv. Initial momentum is minus mv0 and m0 because that fellow does not have any initial velocity. Now this thing is the change in momentum of these guys. But r times that must be the change in their angular momentum taken taken in the same direction. Okay, so it is minus of angular momentum final. Well, this one's angular momentum about the center, not here. Initially it is not yet rolling.
It's only given
Right? It's not rolling. It is, but it is not slipping either, right?
but we are considering that instant when it was given V0, then you won't have any. Rolling, right?
No, my point is it's not yet, does it have an omega? It should have an omega, right? Because this kx is a very large force. This is immediately it is given V0 and there is no slipping at all. Is that what is given in the question?
Ground to prevent slipping at all instants. It's given.
It is given. So that means instantly this will produce a huge force. So that initial part will also be an important part then. So then if I am saying I have given it V0 with the ground preventing it, that means it already has an omega of V0 by R.
I don't get it. Why can't you just give a V0 and then check it at that instant? Why do you have to?
No, because this friction is very large at that instant.
But you've just given it, right?
What do you mean just given?
You just gave the V0
Uh,
and then like in the previous question you just place it. So initially you took omega 0. I mean.
no, but in that case friction was limited, no? Here it's unlimited friction. So if you have an unlimited friction, even within the small delta t, you will produce enough angular velocity to lower. No, so the question is what is V0? Is it after I have given it and it has come to a position where it's no longer slipping, or before I gave it? See, that is the problem. The point is, so think of it like this, right? So imagine a situation, let's take this question. Suppose I had a ball that was stuck to this fellow, right? Now imagine that was a mass that was already stuck. So if I gave this fellow a velocity, this whole rod has to turn. Okay, so whenever I gave that velocity, the velocity includes the fact that I can't just simply push it with F and expect that this will get a velocity, or I can't give it an impulse and expect that this will get a velocity, because the impulse should be such that this will get a velocity, this will also turn. On the other hand, if I tell you that I am throwing this with an impulse such that it has a velocity V0, when it comes and lands here, they hit each other, there is a lot of other stuff happening, and then this starts to rotate. What is this guy's velocity? Won't be V0. It will be less than V0. Now with the new, let us call that V dash, with that new V dash, you can figure out that this whole thing will move in a particular way. But I am assuming that it was given a velocity in such a way that it was never slipping. So the first time you gave, itself the V naught included. If you start saying that actually I lifted it up, rotated it and dropped it, it will no longer be V naught, it will be a different answer. So that means I'll change this number. So I'm going to assume that the V naught that was given is inclusive of the fact that it is not slipping. So that means I probably had to exert a force, and there was this force. I exerted such a large force that the compensatory effect was at the end V naught. After my force and the friction force, gave it V naught and gave it a V naught by R. Okay, so I is mr square by 2, and what is this guy's original omega? V naught by R. It's very important to understand that this V naught is with the rotation, because without the rotation, like you are saying, we can give a V naught. But if we did that, then this won't be V naught, you'll have to change the number. Okay, but we will assume that it was V naught there. So this is I omega. That fellow's, this is the final, no? So I need to write final minus initial. Actually, let me do one thing. Instead of writing final minus initial, I'll do initial minus final. So then I don't have to put a minus sign. So what is the initial? mr square by 2 into V naught by R. This is initial angular momentum. That has 0 initial angular momentum. Okay, let me ask one question now. Okay, so this guy is already rolling. Why is it changing after this? It's already rolling, right?
Yes.
So why should you have friction, etc., to make it change?
Because
V naught will change because there is friction.
Because as I start going closer, there is going to be friction. Okay, except for the instantaneous force, the rest of the forces will basically be to ensure that this, if for example this was not there, then you don't have to worry, it will just keep moving with the same V naught. Because there is spring now, you have to worry about that also. So what about the last part? Finally, what is going to happen? This is going to end up with a V, that is going to end up with a V. So m r square by 2 V by R into 2. Okay, so this gives us one equation that we can now solve. Let us get rid of one R, and let's get rid of this R and this R, and then you can get rid of this R and this R, and similarly here. Okay, so straight away we have an equation which is 2mv. M also we can cancel. So 2mv, let's bring it to this side, 3 by 2 mv naught, and this side I have a minus mv, which will land up on this side and become 3mv. So v will be v naught by 2. This is okay? So you can directly use this idea. You know this idea already, you have been using it, or right? You'll put that ft and do, right? But keep in mind that the change in momentum, linear momentum, is directly related to change in angular momentum when you have a situation of this kind. But this tells me what is going to happen in the final case. But now there is also a problem of energy. What is the minimum compression? Maximum compression. At that point, energy is conserved. How do I know energy is conserved?
Energy, because there will be no friction after that.
So, not because there is no friction, because though there is friction, it is not slipping. So, work done by friction is 0. Okay, so if I take spring force, that is work done by the spring force, but that's spring energy. So, if I count spring energy and then I count the energies that these guys have in the beginning, then I don't need to worry about energy loss, because there is no work done by friction. So let us just apply energy conservation. Okay, so what does energy conservation tell us? So what is the initial energy? Half m v naught square plus half I omega square. Omega is v naught by r. So v naught square by r square. Okay, yeah, you can start with this point and say I am going to do that, but I'm just going to leave it like this. So equal to, both of them in the end will have the same amount of energy, and that will be how much? Half m v square plus half m r square by 2 v square by r square twice plus half kx square, where x is the maximum compression. Okay, now we already know v is v naught by 2, so I can substitute that in here. This will cancel out, this will cancel out. This is going to give me, let's actually cancel out the halves everywhere. So this is v naught square, and this is half v naught square, m v naught square. So this is 3 by 2 mv naught square minus, this is again mv square, half mv square and mv square is 3 by 2 into 2. So this is 3 mv square is kx square. But v is v naught by 2. So if I substitute for v equals v naught by 2, I'll get v naught square by 4. So 3 by 2 minus 3 by 4 is 3 by 4 mv naught square gives me kx square. And so if I simplify that, this, what is the answer? X is equal to, let's take the root. So it is root 3 by 2 v naught root of k m by k. Right? Or you can take the 3 inside, probably it's written like this, v naught by 2 root of 3m by k. Okay, is that the answer? Okay. So now, actually if you notice that root of m by k, that tells you something about SHM. Right? Root of k by m will give you something to do with SHM, right? Omega. So you will see that this will actually keep oscillating back and forth. Because when it gets to the closest point, there's a lot of force acting. So actually as it continues to roll, this guy will basically start to move that way. So it will roll like that, minimum. Minimum will be when they are the fastest. Then they'll continue moving a little further. Then this guy will basically, this will increase, this will continue to increase speed and that will finally slow down and stop. And then that guy will start to come back. So you'll have to, it'll get stretched out and then it'll come back again. So you will end up seeing that this thing is going to keep oscillating. Let us not worry about time period of oscillation for now. Okay. We can't say it is directly simple harmonic motion, but I think it will be. Just a guess. Okay, but my feeling is it will be simple harmonic motion because there is this kx hanging around. It keeps it linear. And why do I think it will be simple harmonic? Because see, energy is going between the spring form and the kinetic energy form. It doesn't matter whose. And since it is constant, if I write kinetic energy, okay, and spring energy is only going to be half kx square. And if I go into the center of mass reference frame, I'm only seeing this. It will be SHM. See it from the center of mass reference frame. This guy's velocity is v by 2 and this guy's velocity will be v by 2 like this. So they are doing this. Okay. So you can cut this off. Actually, you can just do the same problem by putting a wall there and saying that this guy is coming and going because the center of mass is not moving. That's another way of doing it. There you will be able to find that it will be an SHM question. Basically, if it adds up this way, if the spring energy was approximately like half kx square, approximately, it was not perfectly half kx square, then it is going to be, you need small oscillations. Whereas when spring is actually exactly half kx square, differentiate it, you are going to land up with kx as the force, right? So it will be perfectly SHM. So if you put a cut here, it will basically go back and forth. So relative to this is what you will see. But this whole thing won't actually sit here because overall you see the center of mass has a velocity. So it will go there and it won't come back here. It will continue moving, but it will do this and continue moving. Massive problem. Okay, so let us go to the next one. Erase pannilame.
Sir, you were saying, suppose it were not rolling in the beginning itself.
That's பாட்டுக்கு போய்ட்டோம் live ல. Just quickly erase it. Yeah, go ahead.
It weren't rolling in the beginning itself.
It weren't rolling in the beginning. Correct.
Say f is like not unlimited. It is limited but enough to prevent rolling.
It's not possible.
Flipping.
Not possible. Not possible. Not possible. Good point. Good point. Good point. Can you just leave it like that for a little while? No problem. After that you can erase. So Aras Balaji's question is, can I give this guy, can I ensure that there is friction which is not infinite? It's finite friction, but this guy has a velocity in the beginning, so it's not yet touching. And there is only finite amount of friction. So because this guy is going to now move that way, so there's a finite amount of friction. and then can you ensure it does not slip? Not possible, because at this point this guy has a velocity v naught. But as soon as I touch, it has a velocity v naught. I have to make v naught into 0 within 0 seconds. What is the momentum change? Huge, right? You need a huge force to be able to achieve this. Otherwise, even if it took like a very small amount of time, let us say 0.001 seconds, during these 0.001 seconds, v naught to 0, it kept traveling, right? So this point will move from here to there. Because at least it will have some velocity, average velocity. Let's assume it is v naught by 2. It may not be uniformly decreasing. But if we assume it is uniformly decreasing, it will be v naught by 2. Otherwise, v naught by 3, v naught by something, some number. So this is going to be my average velocity into this time. So it will definitely move. The only way it cannot definitely move is you make this time 0. In which means you have suddenly changed the velocity. This would have been a huge ft, huge f, small t. Okay, but that is going to change this immediately, and it will also produce a rotation immediately. Okay, let's think of a question like this. It's an easy question to do. So suppose I had a ball and I have a wall here. Okay. Now this ball I throw with a velocity v naught. This distance is given. Or actually distance is not given. Let us say that if I threw it from the top, it never hits the ground, it goes and hits that. Okay. So when it goes and hits this, let us say it takes time of t seconds. Now I bring it close to the ground and I just release it just as it's up, just above the ground. How much time will it take to go and hit the wall? Can you try it? Oh, no, what I'm saying is I have a ball. So this is the ball. I give it a velocity. There is a wall standing there. Now if the ball is moving at the top, now this ball has been thrown with a velocity v naught. It goes and hits the wall. It takes time t seconds. Now this ball is basically given this velocity just above the ground. You give it a velocity v naught. How long will it take to hit the ground? I mean hit the wall. It is infinite friction. It's a very rough floor. You cannot slip. So how much time? I don't need it. It won't be the same as t. It's a disk. I mean, you can think of it as a disk of radius r. If it was a sphere, it will be a different question, by the way. If it is a ball, it will be a different answer.
It will change because of that.
Because it will change because of the I. Okay. So can you just erase this part? The question out it. So are people able to see that live this thing?
Yeah, yeah, it's much clearer.
Anybody know? Anybody is able to, like if they want, they can comment there or they can put it on the. Anybody has asked any questions? Can you show it to me?
No.
No question.
As of now, no question. The app is done by now.
இல்லை நீங்க போனா தான் தெரியும்.
அங்க போய்
லைட் சாட் மட்டும்
லைட் சாட்ல எதுவும் ஸ்டூடண்ட்ஸ் இல்ல குரூப்ல இருந்து பாருங்க குரூப்ல மானிட்டர் பண்ணிட்டு
Root of 3 by 2 times t.
இங்க பாரு இப்ப லைவ் ஸ்ட்ரீமிங் which oneலாம் கேட்டுட்டு இருக்காங்க. actually make it clear.
அவரோட क्वेश्चंस போட்டுருக்கிறது வந்து it was not that much clear அக்ஷயோட क्वेश्चंस எல்லாம். He has asked some 3 questions. யுவன் போட்டுருக்கிற क्वेश्चंस கொஞ்சம் clearer இருக்கு.
சரி.
நான் மானிட்டர்
இல்ல அங்க இன்னும் ரெண்டு மூணு இதுல இருக்கு. ரெண்டு மூணு ஸ்ட்ரீம்ஸ்ல இருக்கு. ஆ?
Root of 3 by 2 times t.
Root of 3 by 2 times t. Why? When this fellow comes and hits, you just saw it now, right?
I did a conservation of energy there.
You don't need you just use momentum. Okay. You just use the fact that the change r times change in momentum is minus change in angular momentum. Okay. Now final, this guy has a velocity of v, has omega which is v by r. Okay. So angular momentum change is mr square by 2 or 2 by 5 mr square, whichever, assuming it's a ball. Right now we'll just assume a disk. So this initial minus final, initial angular momentum was 0. Final angular momentum is V by R in this direction. Okay, this direction and this direction we're going to assume is a consistent direction. Okay, and then what should I do with R? Change in momentum. M, initial V is, this is final minus initial, V minus V naught. See, otherwise you can go ahead and put Ft and so on, but you don't need all that. So if I did that, Mr cancels out, and that this R and that R will cancel out, so giving us minus V by 2. So bring it here, 3V by 2 is V naught. Okay, so that means this V is 2V naught by 3. So this is the same distance. So this, well, it's projectile motion when it's in air, no? So that means you don't have to worry about gravity. So this takes V naught by T. V naught into T. So this distance is V naught into T, but this is 2V by 3. So therefore this divided by, so time, new time that it's going to take is V naught T divided by 2V naught by 3. So 3T by 2. It will take more time.
Sir, like you said,
You're conserving energy. எங்கேருந்து கட் ஆயிடுச்சு?
கட் ஆகல சார், கட்டுன்னு ஆகல.
ஆ,
ஒன்றும் ப்ராப்ளம் இல்லை, ஜஸ்ட் இது சேஞ்ச் பண்ணால் ப்ராப்ளம் இல்லை, ஆடியோ வந்து இஷ்யூ இல்லை. நீங்கள் நாய்ஸ் கூட வராது சுத்தம். இது பக்கத்தில் சரி சார், செக்.
ரெடியா? இந்த லைவ்ல கேட்டுக்கோங்க பசங்களுக்கு, everybody is able to hear. Right. Okay, because this is an useful question. So question is, when I keep this object, suppose it suddenly changes its velocity or angular velocity, why do we have energy not being conserved? Actually, you should ask the same question if I have two objects that collide and stick. It happens immediately, right? How come energy is not conserved? Because you're talking about F into X. No, but I know why heat. F into X. Okay, but overall just think like this. Just let's take a simple idea of a bullet that goes through a block. Now the bullet, let's assume, goes through the block so quickly that not much distance has passed. But inside the block it would have traveled some distance, right? Overall what is going to happen is the bullet starts there, the block starts here. There is going to be a force on the bullet, which is huge force, and there is a corresponding force on the block, which is a huge force. Now the force acts for time t, but the time is the same. And so in that time, this fellow's momentum and that fellow's momentum change equally but opposite direction. Momentum is conserved. But in the same time, actually what is going to happen is that the block might have moved this much distance. X block. But in this time, the bullet is not going to basically move this distance. It's not going to land up there. The bullet would have actually traveled in and maybe gone that far. The bullet is inside the block. It has all happened in very short time. In fact, if you reduce the time, what is going to happen is this X block is going to keep on reducing and it's going to happen there. But whatever happens, it's still going to go inside. Now, the bullet has moved this much distance. X bullet. Right? So, during this time, the work done on the bullet is the huge F into X bullet. Work done on the block is F into X block. And one of them is negative. This will be negative, that will be positive. So the bullet has lost a lot more energy than the block has gained, because the work done on the block will increase the energy, kinetic energy of the block, which is true. But the work done on the bullet is negative, and that's actually loss. This loss is more than that. What will happen if I increase F and make it infinity? This will become 0. But what about the product? Product doesn't become 0. So because infinity into 0 is not easily decided, right? But if you keep increasing this, this will keep decreasing such that the product will remain constant. Okay, so if I say that this was 10 and this was 20, you can do this by doing it slowly, you can do this by doing it very quickly. If you do it very quickly, this will still be 20. This will be 0, that will be infinity, that's all. So what is the loss? Still minus 10. Now the same thing happens when I try to drop this fellow, because though there is a huge force and there is therefore instantly the velocity has changed. There is no time. It doesn't move much, but it's a huge force into that small tiny distance. As I keep increasing the force into the distance, force becomes large, distance becomes small, product remains constant. That's the loss. Because the distance is that way, force is this way. So definitely energy will be lost. So any lots of these sudden changes, energy will not be conserved with large forces generally. Okay, here is an interesting question related to this idea. So why don't we try this? Okay, actually, why don't we try this question? Why erase panni vittalama? Tirumbi, sorry. So, full of erase. இந்த சைடும் பண்ணு. See, so guys, if you have doubt, please send it on the app. Otherwise, are you also monitoring the live this thing? YouTube. You can also look at YouTube live. You can also comment there if you feel that's convenient. Questions இருந்தா அது மட்டும் எடுத்து கொடுத்துரு. போட்டுருக்காங்களா? போடல ஓகே விடு. போறோம் விட்டுருங்க. It's okay. Don't worry. Sorry. So now let us take this question. I have here an inclined plane which is, let's say, fixed. I have a block. Actually, let us take a block like that. Okay, and I have here another block. Let us assume both blocks have mass m. This angle is theta. Okay? If I shoot a bullet into this, there is a bullet being shot like that. It also has, let us say, it has a mass of, let us say, m. Well, it's a very large bullet. Okay? Or if you want, let's make that m by 3. Okay, dense mass. Okay, that's simpler because we'll just assume that it is mass m. So there is a bullet of mass m that is shot with a velocity of v naught. This way. Okay? Versus this bullet is shot this way. You can shoot the bullet this way or you can shoot the bullet that way. Correct? What is the difference when this guy starts to move? This will start to move. Okay. What is the difference between the velocity with which this guy will move when it is shot from up? So let us call this guy's, call this A. Velocity of A, the first velocity A gets. Okay, first velocity, that means as soon as it starts to move, it will have a velocity, right? What velocity does it get when bullet is shot from the top by velocity of A when bullet is shot from the bottom?
Is it even going to get a velocity when you shoot from the bottom? It's just connected by...
When it first moves, this is a frictionless surface. No, wedge is fixed, wedge is fixed. Will it be the same? Okay, actually I'll make this problem little easier. Okay, wait, we can do this finally, but I'm saying let us do this a little easily, more easily. Okay, so let us take that I took this rod, not the bullet. I kicked this in such a way, this guy got a velocity v naught. Forget that m naught and m by v, etc. I gave this guy a velocity v naught versus I gave this guy a velocity v naught. What is the ratio of the velocities of m when it starts to move? This is a very easy one, but after this you can do the bullet question. So there is no bullet now, I'm just giving it a velocity down. So I take this rod and I hit it in such a way this guy gets a velocity v naught. No friction. won't go and cross over and all that. It will assume this will go up and come back.
Should be one constant acceleration. Like it's like that projectile you throw.
Correct, it's a constant acceleration.
Comes back to the same point, it will have same velocity.
Correct, that's all correct.
1:1. So it should be
No. It's not 1:1.
then like.
And I also want you to
Oh,
tell
fine.
I also want you to tell me
Why? Okay.
why is there an energy loss?
Because when you hit it there with V naught, it was a collision type of problem, wherein you were giving an impulse to two blocks, like sort.
Correct, exactly. So when I'm hitting it with a force, I'm giving impulse to this and that. So actually I exerted more force. Okay. So what happens is this guy also gets a velocity V naught. Okay. Whereas when I hit it this way, this guy gets a velocity V naught, that guy doesn't have a velocity. It goes up, comes back. When it comes back, it has a velocity V naught this way. And now if you think of this force as F, that is F, you can use the bendy axis approach to say F into T must be the change in this momentum, F into T must be the change in that momentum. It is exactly like a collision problem. So that will have a velocity of V naught by 2. So therefore the ratio is V naught by 2. So it is 2. Okay. Now the question is, what if I shoot with a bullet?
Wait.
Now you have to think.
Bullet is
Because
having
the difference is when I'm hitting it with a rod, what I'm doing when I'm hitting it down is different from what I'm doing when I'm hitting it up. By the way, please tell me, when it comes back and this fellow starts to move, right? At that instant, suddenly this guy is jerked forward. It has velocity V naught by 2. What is this guy's energy? Half m V naught square by 2. Half m V naught square by 2. The total, if you add up, will turn out to be half of the total energy. V naught square by 2, V naught square by 2 will be V naught square by 4, plus V naught square by 4 is V naught square by 2, half m. So you will get 1 by 4 m V naught square, whereas original energy of this guy was m V naught square by 2. So now you have m V naught square by 4. Where did the energy go? This is frictionless.
when you give that impulse once again.
Went into the energy of the string, because you take a string and suddenly pull it, you will get the oscillations on a string, right? So you will end up with string oscillating. So the string takes away energy by actually oscillating. If the string was moving slowly, you can ignore oscillation. But you take a string and you suddenly pull, it will. Let us check if there is a string here.
Sir, excuse me, sir. I'm going.
Okay, see you. Is there a string? Good, good. So let's take this one. Hey. Okay, so if you look at this, see, as long as it's moving slowly, you can ignore all the effects, right? But if I had something that did this, there is no way you look at that what is happening. Look at it very closely. I don't think you can see it there. If I did it here, you can see. You cannot ignore that. There is an oscillation.
But it has some mass, right? Usually
It doesn't matter. I am saying if you're thinking of a string cannot exert this large force without, like, look at this. It's a huge force. With such a huge force, this oscillation will carry. It has to take away some of the energy, even in the ideal case. It is like when you're doing capacitors. In the best case scenario, you can't decide to go this way and expect that you will find that the work, suppose this was plus and minus, E dot dl positive. If you assume it was 0, you can't have laws of electrostatics working if you don't assume that the field has to bend. Otherwise, you have to make it infinite. If you make it infinite, in which case you'll never be able to go around. So you can't do both. The same way, this will definitely have to lose energy. It goes off into the string. Okay, what do you think will happen if I push it with a bullet?
There will be a loss because of inelastic collision,
Correct.
and then also loss because of this way that you took.
So will it still be the same total loss?
No. Sir, because it will act as a 2m block there. It will be like previous case, but that block will become a 2m block.
Okay.
So it will be initially this will be 2m and it will have an momentum of mv naught and then conservation.
But I'll tell you that it will be the same. Let's think about why.
the loss energy is the same.
Just forget the loss. Forget the loss. This is the momentum in this direction. and no amount of momentum in this direction is never going to change. Okay, right now this guy is going to get how much? V naught by 3, because this and that will have to share it. That is the initial, okay, where I'm shooting it from the top. So the top is going to be V naught by 3. But when I shoot it from the bottom, these two fellows will share it. So they will end up with a momentum of m V naught. Total momentum, 2m V naught by 2. But when it goes and comes back, it has Vm V naught. Now it will have to be shared between 3 of them.
By 3 V naught by 3.
Correct, you will again get V naught by 3.
So then the answer is 1.
Correct, answer is 1.
Sir, but you said it is same as last case answer.
No, I didn't say the same as last case. I said the case like this and the case like this will end up being the same.
Last case, when you hit it, after hitting, you got the V naught.
Correct. So the difference is here, my original momentum was mv naught, and this momentum was mv naught, which becomes this momentum, which is mv naught. Okay, gravity gives that extra. But earlier when I was hitting with the rod, I actually exerted more force this way than I exerted that way. So the momentum I gave this way was actually larger than the momentum I gave when I was giving it that way. Right? So that makes a difference. Whereas it will step by step, if you work it out, when you hit this guy will get V naught by 2. When I hit it like this, V naught by 2, V naught by 2 goes up and comes back, V naught by 2, but it is 2m into V naught by 2 downwards, must be 3m into V naught by 3 along this axis. Is that okay? Okay, right. So, sorry, erase panni vitturunga. Okay, so let's go to some other question. What is that you are doing? That is your passcode, not like a simple Z or something.
It's the same.
But you're using 2-3 fingers.
I'm using multi-touch, so I don't have to slide it all the way. Touch
Okay.
both and then it gets the link.
Okay. இன்க்ரீஸ் பண்ணிடுங்களேன். இல்லை நீங்கள் நிறையவே இன்க்ரீஸ் பண்ணலாம், என்ன ப்ராப்ளம்? இந்த மைக்லேருந்து தானே பிக்கப் பண்ணுது, எல்லாத்தையும் பிக்கப் பண்ணுமா? சரி, see அந்த வாட்ஸ்அப்லையும் செக் பண்ணிட்டு என்னோட just open that and see. Let's see if anybody has asked any questions.
So pressure and temperature linearly.
Sir, have you started? Oh, all these guys have asked all these questions. Okay. Right. Okay, so let us try to answer this question. There is a cylinder of volume 10 to the V, which is 10 to the power of -2 meter cube, right? This is that thermodynamics question that was posted on the group. There's a heater and all that. There is a partition. The cylinder is divided by a thin fixed membrane. The conducting walls contain 8. What is the conducting walls?
Non-conducting.
Oh, correct. I was wondering what is happening. Okay. So this whole thing has volume 10 to the power of -2 meter cube, made by non-conducting walls containing 8 gram of helium gas. So 8 gram of helium gas. Helium is monoatomic. Okay. The cylinder is divided by a thin fixed membrane into 2 unequal parts. Volume of the left part is V by 3 and volume of the right part is 2V by 3. The left compartment has an installed electric heater. Okay, and due to finite conductivity of the membrane, heat passes from the left part into the right part. So it basically heat transfer happens that way. heat transfer rate through the membrane is 0.2 watts per delta T per degree. Okay, so this heat transfer rate is 0.2 watts per degree Celsius. Okay, across the membrane. So we are going to assume that when this is happening, it's inclusive of the entire area.
Yes, correct.
Because this is the total power, right, that's getting transferred. Power per unit Kelvin, right. Initially the heater is off and both parts are in thermal and mechanical equilibrium. What is mechanical equilibrium? P naught is P naught in the beginning and T naught is T naught. I'm assuming naught means in the beginning. So P naught is equal, T naught is equal in the beginning. And let us see. The membrane can withstand maximum pressure difference. So delta P max is 10 to the power of 3 pascals, 1000 pascals. Heater starts applying heat slowly to the left part at its maximum possible power such that the membrane remains intact.
R is given.
This is delta T is given, right? This is per delta T. It supplies heat at the maximum
Possible
power. So Q, which will be 0.2 delta T. Right? Because it's 0.2 watts per delta T, it is going to supply at the maximum possible, which will be 0.2 delta T. Depending on what the delta T is, such that you will have pressure maximum of that.
dq by dt is 0.2.
Okay, that's what I'm saying. No.
Maximum rate of
No, it says the heater gives some heat at its maximum power. It's
No.
not like the transfer between
Rate
left
is
to right.
point. Rate depends on temperature.
It depends
Oh,
on
sorry.
temperature.
This is the power by T. Even this is not Q, no, this is Q by T. Okay. So left compartment, okay, after a long time, such that the membrane remains intact after a long time of heating also. So what is R? 25 by 3 joules per mole Kelvin. Kelvin, Celsius and all that is fine. So what is the question? Question is, for the left compartment, what is the rate of transfer of heat? For the right compartment, what is the... So basically we have to do a matching, right? Okay, let us try to first figure out a little bit more before we answer the question. Let us think about what do you think should be the pressure difference? The pressure difference should be this, maximum. Okay, because if I increase pressure, now the volume can't increase. So if you go with PV equals nRT, now it had 8 grams, right? 8 grams for the whole volume. Now 2/3 will be sitting here and 2/3 will be sitting here and 1/3 will be sitting there. 8 grams of helium. Helium has mass of 4. So how many moles is this? 2 moles. Of the 2 moles, 4 by 3 moles will be here and 2 by 3 moles will be here. Okay. So if I look at this, the pressure on the left side, so let's calculate. This is 2 by 3 moles. I'm going to say V by 3. So pressure on the left is P into V by 3. Okay. And so we will call this PL and that we will call PR. Okay. So this N is, how much is the N? 2 by 3 moles into the current temperature, whatever the temperature is. Similarly, PR into 2V by 3 will be 4 by 3 RT.
The T's will be different.
So if I cancel this out, T dash, yeah. So this, let's call it TR and let's call this TL. Okay, so if I now look at this equation, well, this
instant are we writing it for?
any instant, because PV equals nRT is true for any instant, right? So if I now try to rewrite this, I can say PL, cancel this out, it is 2R by V TL. PR is 2R by V. Now you need this because otherwise it's going to be tough. So it's good for us that it's exactly like this. So now if I do delta P, it is 2R by V delta T. But the maximum, therefore, pressure difference will tell me what is the maximum temperature difference, and so then we are done. Okay, so maximum pressure difference is 1000. So 1000 times V, is V given? 10 to the power of minus 2 by 2 times 25 by 3 is delta T max. Delta T max into 0.2 is going to be the rate at which power is getting transferred. 0.6, why 0.6? Oh, it's calculating, okay, fine. This is 50, right? So 50 means this is going to be 20. What is 30 by 50? Okay, correct. Okay, yes, thanks. But just give me 1 minute. This is 60 means 0.6, correct. So this is 0.6 degrees Celsius. Kelvin doesn't matter, the same Kelvin Celsius. Okay, so if this is 0.6, if I multiply by, no, this is not, this is 0.6. Is that what you were saying? Okay, so maximum power which is getting transferred is 0.2 times 0.6, which is 0.12 watts. So is there an option like that?
Yes.
So there is a point, yeah. So for A, the option that was available is S, right? So for A, it is S. Oh, there's one more. Okay. Rate of transfer of heat 0.2 is wrong. Rate of transfer of heat 0.06 is wrong. Rate of change of internal energy is constant. Let us think about that. Well, if I am supplying heat at a constant rate, that means my temperature is increasing at a constant rate because only constant amount is getting transferred. So that means energy is increasing at a constant rate, but energy is basically directly proportional to RT, right? So 3 by 2 RT. So therefore, yes, so that is also true. Rate of change of internal energy is constant. So T is also correct. Not that T, this is a different T. P. So pressure of the system versus temperature of the system. Yeah, you can look at this. Delta P is constant times delta T. So it's a straight line. But let's hold on. Does it pass through the origin? If temperature is 0, pressure should be 0. PV equals nRT. No, because it's, yeah, if it's in Kelvin. Huh? Correct, because, but okay, it will never become 0. So the graph really is this. It starts there and goes on like this.
That's what they have given dotted lines.
Oh, there is a dotted line there. Correct. So this is the correct graph. Correct. So P is also correct. So S, T and P. Now what about B? For the right compartment, also pressure and temperature, this thing is correct, right? So for B, you have P which is correct. S, rate of transfer of heat is the same. So this is also correct. What is that? S. The rest of it, rate of change of internal energy is also correct. So T. For the whole cylinder, well, for the whole cylinder, sorry, what?
I think for B, it should be R. R is also correct, I think. Because if you multiply 0.2 into...
Rate, no. That is the answer. This is point.
Whatever you give,
Wait, for
Correct.
the right side, right? Okay, fine.
For the right side and right side, whatever is heat transfer is a heat transfer, right? So that is okay. No, but the heat transfer for the, wait, for the left compartment, what do you mean by rate of heat transfer? That is not correct. That is not correct. That is not correct.
You did it for the whole system.
No.
Or you did it
No,
for
this
the
is, no, this is only to right, to the right. Only to the right. This amount that is getting out, right? But how much is this guy increasing is also something we have to calculate, no?
But this guy's increase in T.
What is given here? 1 second. How much the heater starts supplying slowly and the transfer is 0.2. Okay. No, but if this is the amount to the right, that means this guy has to, But how much is the extra?
Only option
Should be
match.
0.0.
Huh? No. Whatever heat comes in minus whatever heat goes out must increase the temperature. No.
We know the
P should be
temperature.
same.
We know the temperature. So 3/2 RT would give the answer, I think. Using change in.
It's not 1 mole, no, 2/3 mole. So 3/2 into 2/3 RT. Okay, so basically RT. RT is the internal energy for the gas, right? Now but I'm adding some heat and I'm supplying out some heat. So the heat that comes in is, let us say, let's say power 1 that is coming in is something, power 2 that is going out is 0.12. Okay, so power 1, or let's call it PO, power 1 minus 0.2, 0.12 will be the rate of change of this, which is R into dt by dt. Okay, but this change must be equal to this change. But hold on, because now what is this delta P between these two fellows?
It should remain a constant. It should
But-
remain at 10 power 3.
But hold on. Is the dt for this guy? This is not the delta, same as delta T. Is the
For that side also we can take.
no, 1 second. Since this is a maximum already, right? dt by dt, dt L by dt is, why is it 0? It won't be 0. This is equal to this. The difference is maximum. So both of them have the same rate of change of temperature. At maximum possible, the difference maximum possible, no? So they must both have the same rate of change of temperature. Now if they both have the same rate of change of temperature, we know the rate of change of temperature for that fellow. How do we know? Because it's 4/3 moles. So 4/3 into 3/2 RT. Energy is 3/2 per mole. So what is this? 2 RT. This is the internal energy. Rate of change of internal energy, so 2R dt by dtr by dt is equal to 0.12. So R times dtr by dt is 0.06. Okay, so where did we find that? But what was the question? Rate of change of theta. That's the rate of change of temperature, right? But what was the question? Rate of supply of energy, correct, that's what we wanted, right? Rate at which, because transfer in minus transfer out. So we just want rate of change of this, which is R dt by dt for L, but it doesn't matter whether it is L or R, it is the same. But R dt by dt is 0.06. So therefore it is 0.06 watts. Okay, so that means for A, actually which is not correct, S is not correct, R is correct. Okay, so for both P is correct, the graph is correct, and for left component, left compartment, rate of transfer of heat is 0.06. Because actually, so what is happening is this guy is getting in 0.18 and is supplying 0.12. It actually makes sense because this guy has twice the size. So whatever is being received, twice has to go there and one share will land up here, so that they correspondingly keep increasing in energy. Yeah, when looking at this, so it's good. So it is 0.06. Yeah, so this is R is correct, T is correct, rate of change of internal energy is correct. Rate of heat transfer is 0.12. That is only correct for this guy.
Sir, I think you should not be getting T and P for left and right separately, because initially there must be a this one starts supplying, the heater starts supplying heat, but it does not get transferred by 0.12 throughout the process. No, it only starts going by that amount once you develop the DT.
No, it is given it always supplies at maximum power.
Yes, But even if it's
Correct.
difference should have developed, and only then you will start getting
the heater starts supplying heat slowly to the left compartment at its maximum possible power such that the no, what he's saying is in the beginning it is not going to supply a lot of heat to this one, right?
First it should develop the temperature difference would have been zero.
Uh,
Slowly the temperature difference will develop, and then
But does it matter? Does it matter to, because he says after long time of heating.
also, the membrane remains intact after a long time of heating.
So
Once
the
the-
pressure difference initially should itself be 10 bar 3 pascals. Yeah.
No. The heater starts supplying heat slowly. The left compartment. The English is not correct. I am assuming what it's saying is the heater starts supplying heat such that
the membrane
supplying heat to the left compartment such that its maximum possible power, at its maximum possible power, so that they.
I think that part is not required. Right? We aren't concerned about the power of the heater.
No, because then that means very quickly it will supply it, and so instantly it has now got a temperature difference.
I think
But
slowly is maybe
consider
for quasi-static
processes.
process or something.
Correct from this address, but yeah, what I'm saying is that it will supply heat at 0.12 and 0.06 here, sir. So that will be increasing. It is supplying at maximum possible things, sir. Maximum possible rate of heat transfer, sir. It is given at the end. It will always supply maximum possible heat transfer. But the temperature will increase faster on the right hand side than on the left hand side, sir.
No, his point was in the beginning it is P0, right?
Yes, sir.
So the pressure difference is 0, no? When I start supplying some heat, this pressure will increase. So the pressure difference will become 1000 Pascal pressure difference. It will take you some time, no? After that, you can start saying that it is 0.2 delta T.
In that
But till that time, there is a problem. But I am assuming what he's saying is, when you start supplying, immediately it will basically, like in the beginning, this guy is going to supply like a huge amount. I don't think the word slowly is meant there. I'm assuming that was
Might be because they are saying it's
quasi-static. Yeah, correct. But
Okay,
the word
so
slowly
let's
then means that it will take time, no? So we'll assume that basically this has already started supplying to such a large extent there is a quick power pressure difference.
or very slowly such that delta T it kept increasing at the same rate.
But you can't do that, no, because your pressure difference,
must
yeah, pressure difference must be 1000 Pascal, so you'll have to do it fast. Okay, so we'll have to assume that, otherwise it's a mess. Okay, for the whole cylinder, what happens? Let's check. So for the whole cylinder, well, you're supplying totally 0.18. The whole cylinder is just simply heating up. So for the whole cylinder, is the rate of internal energy constant? Yes. What is the transfer of heat for the whole cylinder? It is 0.12. So Q is not correct. Right? Through the membrane, there is a rate of heat transfer which is only 0.12. So this is C and that is D. So for the last part, it is only S, because membrane can't have pressure of the system and all that, right? And for the whole cylinder, it is P. But it doesn't have meaning, no? Because it's not constant across for the system. There are two pressures. It is not equilibrium. So you can't do P. If I combine the two, you can talk about pressure and temperature in thermodynamic equilibrium. Otherwise, it's a non-equilibrium system. If you take the whole system, that's why there is a flow of heat inside. This whole thing taken together is not a system. I mean, it's a system, but it is not in equilibrium. So we can't talk about the PT graph for the particular, if you take it overall.
is not uniform. Right?
B is not uniform, so you can't talk about that.
But in both sides, P is proportional.
But rate of internal energy change, you can definitely say, so T is true.
They'll be in equilibrium, but you won't have.
That's all, only T. 0.18 is not correct there, so only T.
Sir,
Okay,
but in
yeah.
both cases, P is proportional to T, no, sir. Finally, also I should get.
Correct, but you can't talk about P for the entire system, no.
But if both are similar, let's say some P, some T will come, sir. But there will be same ratio, no, sir. P by T.
No, but who's P?
Some P total will say. Sir.
But you can't talk about a total P. See, you're talking about the ratio being the same, but you can't talk about pressure because pressure is not uniform. This has a different pressure, that has a different pressure. Right? So, okay. So,
It matches.
huh?
It's fine.
What is fine?
The answer key is.
The answer key matches with this, you're saying. Okay. Okay, so this is clear? One more question? Anybody's asking any question?
Yeah, Sharath is asking.
Let's finish that. What is this? Let's do this one. This is an easy one. What is that question?
Magnetic.
I'll do whichever is easy.
The magnetism-based question.
Magnetic question. Where is the sorry. Okay, let me just finish this one. You can erase this. Who has asked that? Sharath has asked?
Yeah, Sharath.
Okay. So Sharath, I'll just take your question. Whose is this question?
RS Bharat.
You ask this question. You're asking too many questions.
Accumulated over 1 month.
1 month questions, is it? Okay. A particle. Huh?
What we did
Correct.
before.
Correct. No, I'm happy. Now, I think this in the app you guys are answering questions quite well, right?
Yeah.
App you are able to talk and answer the questions, right? Okay, good.
Magnetic field, இப்போ Sharath கேட்ட question.
எந்த
இது ஒரே செகண்ட் இது ஒர்க் ஆகுதுன்றதுலமா எரேஸ் பண்ணிடுங்க இல்லைங்க பண்ணி ஓகே தேங்க் யூ okay so let us look at this one. Actually it's a very interesting one and easy one. Okay, so I like this question. There is a particle of mass m that is projected from the ground. Okay, mass m is projected from the ground with an initial speed of u naught, making an angle alpha with the horizontal. So this fellow goes like that. At the highest point, what is this fellow's velocity? U cos alpha. At the highest point, it has a completely inelastic collision with another identical particle. So that also has mass m. Okay, now this identical particle was thrown vertically upward from the ground. Well, that means it must have been thrown from here with initial speed u naught, same u naught, but it was thrown vertically up. Do you think when this fellow reaches there, its velocity will be 0? Vertical velocity? This guy's vertical velocity is 0, right?
No.
This fellow's.
That one's 0.
What about, let's not write 0 meters per second with too many m's. So let's say that was 0. What about this guy? This guy's horizontal velocity is 0. What about this guy's vertical velocity?
Times 1 minus sin alpha.
Let me think. Okay. Now this guy, you can sit and calculate all of that. Sandeep, Jandeep, look, listen. You can calculate all that, but look at this guy's kinetic energy. What is this guy's kinetic energy? Half m u naught square. What is this guy's kinetic energy? Half m u naught square. What are their potential energies there? Same. So they must both have the same speed. So this guy must have a velocity of u cos alpha. So when it collides, this guy is going to end up, both together will end up with a velocity of u cos alpha by 2, and this direction is going to be u cos alpha by 2, and so the angle will be 45 degrees, pi by 4.
It will be a different U though.
Why will it be different u?
Because after they collide, they lose energy. It's an inelastic collision.
No. Momentum has to be conserved, right? So this guy has a momentum this way and that guy has a momentum that way.
U by 2.
I have taken u by 2.
Sir, இங்க எதுக்கு u cos alpha? U by 2.
Okay.
I have done u by 2.
Before collision.
I am saying this guy and this guy will share this velocity effectively, and these two fellows will share the vertical velocity. So it is a mass of 2m with a velocity of u by 2 cos alpha plus u by 2 cos alpha. The question here is only simply find the angle.
Pi by 4.
So this is the angle which is 45 degrees, pi by 4. Okay, now the basic point is when this guy gets there, its velocity is u cos alpha. Just keep in mind energy is very useful. So if I am throwing an object from this point, okay, at various angles, u naught, but everything is u naught. u naught, u naught, u naught. Whenever it hits the ground, the time it takes to hit the ground will all be different. Okay, but when it hits the ground, if this guy has a velocity of v naught, everybody will have v naught as the speed, except the angles will be different. Because kinetic energy plus potential energy there is kinetic energy plus potential energy here. Potential energy change is the same, kinetic energy initial is the same, kinetic energy final must be the same. Okay, keep that in mind. This is a very quick way of figuring out about speeds. So when speeds are given, connect it up. Do you think both these fellows would have been thrown at the same time? Suppose the question was, what is the time difference between when they were thrown? Then you can't argue that, because then, look, this guy will have to be thrown a little later, because it will reach here very quickly. This will take a little longer to reach. This guy's vertical component is u naught sine alpha. Oh, I should have called it u naught. Oh, that was the confusion, is it? Okay, it's u naught, not u. Okay, so if I look at this is u naught sine alpha. So it will take u naught sine alpha to become 0, will take this much time. But for u to become u cos alpha, u naught cos alpha, the time that it will take will be u naught minus u naught cos alpha by g. So this will be 2 sine square alpha by 2. Okay, so this is different, very much different from this. So if I look at this and look at one of the signs, the ratio of the times, if I say that that fellow takes t1 and this fellow takes time t2, so this is t2 and that is t1, the ratio will be tan alpha by 2. Well, that is not the question, but time, the time won't be the same. Correct. So time is not the same. Okay, speeds will be the same. Because you want to collide, then this guy has to start a little. Same height, yes. Okay, seri, idu pannila. Can we take that Sharat's question?
Yeah.
Can you also get some water? No. Huh? Erase pending.
Gamma photon is passing through nucleus.
Sorry, what?
You don't want this. Magnetic field question?
Magnetic field question.
A charged particle of mass m.
Easy question, hard question. I can't read the whole thing. It's bending off somewhere there.
A charged particle of mass m and
A charged particle of mass m, charge q.
A uniform magnetic field B acting into the plane.
It's not even a complete sentence. Okay. The plane is frictional.
Having coefficient of friction mu.
Speed of charged particle just before entering the region is.
V naught.
Oh, okay. I understand what they are trying to say. Okay, fine.
The radius of curvature.
There is a charged particle of mass m, charge q, in a uniform magnetic field acting into the plane. So let us say this was the uniform magnetic field acting into the plane. A charged particle is entering it. Let's assume like this. The plane is frictional and has friction coefficient mu. Speed of the charged particle just before entering the region. So it is entering like that. Its speed is v naught. Okay. Coefficient of friction is mu. It has a mass m. Okay. So the radius of curvature of the path after time v naught by 2 mu g. Is that the time?
Answer option please.
T is v naught by 2 mu g. You want to come and do? No. Okay. Let us see. What is the, no, they are asking what is the radius of curvature, right? So we want the radius of curvature after this much time.
Sir, mu will always be acting against the V naught.
Against v naught, okay.
Quarter angle. So force you can add.
No, but this is not frictional force mu, right? Coefficient is. No, coefficient of friction.
So mu g will be acceleration.
Why is it on the ground? Is it in
Horizontal plane.
this is a horizontal plane? Let's just check 1 second.
G.
Horizontal plane is given.
We have text, otherwise there will be no normal force.
But let me just see, there is B is that way, Q V cross B, right? So V cross B, so the force is that way. But the problem is, there will not be any frictional. So okay, well, we are going to assume that this whole thing is down. So there is a normal force like that, N. Okay, so N is going to be mg. So mu mg. Mu mg means there is going to be a frictional force, mu mg. Right? And so that means if this fellow is going around like that, you will keep losing energy. Okay, so acceleration is mu g.
So v minus mu gt.
We can do that. I am going to assume m times mu g into, we can do, we know the initial velocity is v0. After time t, so m times mu g into t is the force along the direction of motion. And so we can then say that is the change in momentum along that direction. M
But the direction itself is changing.
v0 minus v. No, but it's always like when it is here, it is acting this way.
Yes, okay.
When it is acting this way, right? So I'm saying I'll resolve the components along the direction of motion.
Okay.
So along the direction, only the speed will matter.
Can you do that?
Yeah, you can.
No, I'm saying, can you just make it a straight line, because the velocity is not going to change because of v.
That will be radius of curvature.
The speed won't change because of v.
Sorry. Speed won't change because
Correct.
of v.
So basically there is going to be a mu mg this way, and there is a magnetic force that
So
way.
can you consider
This will not change the speed, this will change the speed.
So you can consider it like a straight line.
No, that's exactly what we are doing. I mean, change in momentum.
That-
Well, I would have actually done S, work done, energy. But right now, because T is given, it's nicer. So we can just do V0 by 2 mu g. Okay, so this basically means mv0 by 2 is mv. Okay, or v is v0 by 2. So at this point, you have a velocity of v0 by 2, radius of curvature.
You don't know the path.
Huh? You don't know the path, correct. So I can say m v0 square by 2 by 4 by r, mv square by r. I don't want to use it here. So mv square by r is equal to magnetic force, which is qv cross b. So is the q given?
Q is
How much is q?
Q.
Oh, q. V is v0 by 2 into b, qv cross b. Okay, so if I cancel that out, what do we get? Radius of curvature is m v0 by 2qb. So option what? B. Okay. Okay, so idu erase panikalam. Whose question was this? This was Sharath. Somebody else, Yuvan had asked me some.
He asked the photoelectric effect, and also he asked about spring constant.
Why when you cut it?
Oh, that okay. Let's just quickly do that. That's an easy one. So spring, and he asked about photoelectric effect. Anybody else? Anything else?
Akshay has asked a question.
Surface tension and viscosity.
bubble க்கு double ஆகும் அந்த மாதிரி புரியல.
Bubble can double agum.
Sir, இது வந்து surface tension.
Okay, okay. Sorry. Why does it become 440 by aradhuva? Sorry, right. Sorry. Okay. Let us. Black work ah matendade. Give me another pen. Okay. Is that pen working? Give me that pen. New. Okay, good. Sorry. So, what was the question we were discussing?
Fluids.
No. No, double the bubble. No, what was the other question? No, what did this guy ask? Yuvan asked. Spring. Right. So, this is Yuvan's question, right? So, if I take a spring and I cut it, okay? So, first of all, let us look at the spring, and I am pulling it here. This we are assuming is a massless spring, by the way. Okay, or a spring that is at rest, it doesn't matter. If it is moving, definitely we want a massless spring. So if I exert a force F here, I am also exerting a force F there. Right? It is like a string because it's massless. If there was a difference in the forces, the spring will accelerate with almost infinite acceleration because it's a massless spring. Now at any particular point, what do you think will be for this portion, how much will it be pulling and how much will that portion pull? It has to be everywhere F. Okay, so the portion on this side, like let us think of it, let's cut it up in a slightly different way. So think of it like this and then we continue. It's not like actually there is a split, but just for me to draw. So if I cut this portion, the force must be F. Who is exerting it? This side is exerting. It has to be F, otherwise this will accelerate. Similarly, this portion, it has to be F. So anywhere you cut the spring, you will find that the force is F. Okay. But in general, suppose I had a spring which had no extension. I would have said that the spring force F is 0 when x is 0. If I keep this fixed and I just move this from here to there by x, now both sides the force has become kx. Right? So kx is basically because of that extension. Now the thing is, the force is the same, but if this whole thing has extended by x, that means the extension for this portion will be part of that x. This portion will be part of the x, and if I split it up into 3 pieces, each one has increased by x by 3, x by 3, x by 3. Otherwise, what is going to happen is, these fellows just simply kept remaining as it is, only this portion expanded, which doesn't happen. The whole thing expands, which means actually this portion, if I decide to cut this as 3 pieces, this portion of the total x, this portion expanded by x by 3, x by 3, x by 3. Okay. So generally when a large spring expands, each part of the spring expands proportional to its size. But the movement of each one was only 1/3 if I cut it into 3 pieces, 1/5 if I cut it into 5 pieces, half if it was cut into 2 pieces. But the force on each side is actually equal, because you can see that force is equal. So if this whole thing, this was kx, it is because this entire thing expanded by x, it's already expanded. But this portion has not expanded by x, it has expanded by a fraction of f. So let me say it has expanded by some small amount, x by 5. Okay, well this doesn't look like x by 5. So let us say that this expanded by x by 3. So this would have expanded by 2x by 3, because that is a little longer than this one, or 2 times as long as this one. But for x expansion, force is F. So what is K? F by x. But now for this little spring, what is the force? F. But you got that force when the extension was x by 3. So therefore this guy is K small is F by x by 3, because force divided by extension for this fellow's extension. So this is 3 times F by x, so it is 3K. Actually this is weird, because if you think about a spring and I start to extend it and I decide to cut it into tiny pieces, each of those fellows have a infinite K, because they have hardly expanded, but they ended up getting a huge amount of, equal amount of force. So the force, any cut, anywhere you take, this force, this force, this force, this force, everywhere you will see that the force is the same, but the extension is x by n. So K will be n times the original F by x extension, K. Is that okay? So I hope that is clear. So if I took a spring and connected it with another spring, so this means if this had K, that also had K. Now when you pull this, originally if this was not there, this would have extended by x. Whereas now if you extend this overall, this point goes up by x, actually this will go up by x by 2. So that means this guy's extension is x minus x by 2. It's not really extended. So this guy had a share of x by 2, this guy had a share of x by 2. To produce the same force, how much force will it produce? It will produce whatever usually it used to produce, which is kx by 2. So that means the force that is produced is kx by 2. But you think that this point has moved x, because I am going to think of this as one connected big spring, except its k dash is k by 2. So you connect a lot of springs together in series, the spring constant simply just becomes half. So in general you can do this. K1, K2, you can think of this as one spring. If I call this K, it follows the rule 1 by K is 1 by K1 plus 1 by K2. Why? Because what is constant is F. Okay. What is different is X. What does it look like? In current, it would have been a different story. But if I think of it as capacitors, what is constant is Q. Q is CV, F equals Kx. Right? So if you look at this, the V is different, the Q is the same. So effectively what you are going to get is Q by C1 plus Q by C2 plus Q by C3. This X1, X2, X3, if you add up, you will get total X. V1, V2, V3, if you add up, you will get total V. So the formula for capacitor and formula for series of springs will be the same. What about parallel springs? This will be 1 by K, right? So if I had, on the other hand, parallel springs, K1, K2, K3, if this extends by X, everybody has extended by X, so everybody's force has become K1X, K2X, K3X. So you will end up with a total force of K1 plus K2 plus K3 times X. So this will be the K. Okay? Right. Enough time acha.
Almost 4 hours.
We'll just take another 10 minutes and somebody else had a question?
No.
Stop.
One more question. Akshay oda mattum I guess.
Erase பண்ணி விட்டுரு.
That is
என்னது கொஸ்டின் காட்டு. இல்லை பட் இவங்க ஃபோட்டோ எலக்ட்ரிக் எஃபெக்ட் கேட்டாங்களே. யுவன் யுவன் ஃபோட்டோ எலக்ட்ரிக் எஃபெக்ட் கேட்டாங்க.
How do you make out if like heat is being added or taken away from the system?
Arrow is given.
Ah.
So temperature is decreasing, volume is increasing.
Hmm.
Volume is decreasing, no increasing.
Oh, what does it say?
It says volume is decreasing.
Okay. Volume is decreasing.
Sorry, volume is increasing.
Increasing and temperature is decreasing.
Volume is increasing, so work is done by the system.
Hmm.
Temperature is decreasing, energy of the system is reducing, so obviously
You can't say anything.
you can.
It's
Work is being
Q
done
equals
outside.
W plus U.
What do you mean? My internal energy is reducing.
Yes, and you are doing work.
Now what is the question? Work done by the system is positive, that is correct.
Yes, I got A and B.
Huh.
I'm asking about the heat part.
Okay, let us check. So, actually I don't know how to do this, let's see. So I have here VT and you have given a graph like this. The arrow is important because if it's this way or that way, it's a different story. Okay, so here this is a system of, let's assume this is a gas system, right?
Must be.
Hopefully, otherwise it won't have much meaning, right? So now temperature is decreasing, which means the internal energy is decreasing. Correct, because internal energy directly is related to temperature. Volume is increasing. Whatever is the pressure, it may be not too high, but basically that means there is work done by system. So work done by the system is positive, true. Okay, because volume is increasing. Volume started here and ended up there. Internal energy of the system is decreasing, that is also correct. Is heat added to the system or heat rejected by the system? Well, the total, if I took this as a system, it has, let us say, I supply heat in and it is doing work. Okay, internal energy goes up.
Only if
Correct.
is less than.
So I can't direct, so basically this will be delta U. the plus W, right?
I think we have a relation between B and T.
We can find out. We can find out. So this is generally the case. We can't directly say this because this is positive, but this is negative. So we don't know whether heat is coming in or going out, but we can convert. So what does this say as relationship between V and T? V happens to be some AT plus B. Okay, but you also know that it is a gas, so it must just be AT. But this is a weird relationship. No, it need not be.
V by A plus T by B equals 1. If you want, because it's like this.
I know, but I can increase pressure, right? PVT. So the question is, yeah, this is not a problem. So this is the equation, right? So what about A and B? Are they positive?
A is negative, B is positive.
So, so can I write it like this? V plus AT is B, or
Yeah, B plus A.
no numbers are given, right? So, or you are saying V by A plus T by B is 1. Correct. That's a better way of writing it. Okay. So, if this is our relationship, we want W, right? W will be integral PdV. From this, can I find out what is? Actually, why don't we just? Actually, let's just write it as A minus BT. Because I don't want really V, no? V is A minus BT, or I want everything in V. So I'm going to rewrite this again as T is equal to A minus BV. Will this work? This will also work, where A and B are positive. Because I want PV equals nRT. So PV equals nR into A minus BV. So that is nRA. So let us take, what is P? P is nR A by V minus B. And we want to do PdV. So if I did a dV here, we can do an integral. So what does that give us? nRA ln of V2 by V1, right? Minus nRB V2 minus V1. Correct? Now this is the work done, which is a positive quantity but doesn't help us very much. Delta U is, well, does it say 1 mole of gas? It doesn't say anything. N moles of gas. Doesn't say monoatomic though.
It doesn't say anything. It doesn't even say it's a gas.
It's an ideal gas.
Does it say it's a gas?
I have no idea. It doesn't. You are the one who gave me the question.
Yes, but I can't see the question. Right.
Okay. So,
It doesn't say anything.
doesn't say anything. So let us see. Let me just think a second. If I say U is nRF, let's just say some F, delta T, right? But delta T is minus B delta V. So nRF minus B, no, not freedom degrees and all that. I'm just calling it some fraction. I don't know what F is. So into B delta V. Okay, and let's just check this. NRB delta V, right? Which is negative?
ln of V2 minus V1 difference வந்து V2 minus V1 ஓட கம்மியா இருக்கும்டா. So அப்போ V2 minus
But we just realized work done is positive.
Hello, this is V2. This is V1.
Ln V2 by V1.
There is also a factor of A.
No, but it is V2 and V1.
ln V2 minus ln V1 will be lesser than V2 minus V1.
But it is multiplied by A, that is multiplied by B.
அதுதான் நான் பார்த்தேன்.
Okay. But you know that the work done has to be positive. Okay. Now if we get this, now the question is BNRF. This is BNR delta V. This is, why is there a second BNR? There's only one B. I am getting this from here. delta T is minus B delta V. So there is an F factor, there is a BNR delta V there.
Just for like information,
Hmm.
the key does not say whether it is supplied or removed.
So what?
Key only says the two
Oh.
things which you found out.
So we can't say is the question.
saying.
Okay. Anyway, let's
Maybe you can find out.
maybe we can find. Okay. So let us see Q is NRA ln V2 by V1, and this is minus NRB delta V. This is minus NRBF. I'm adding them, right? So minus F plus 1 NRB delta V. Delta V is a positive number, yes. But we can't therefore conclude that this is positive or negative, because that may be positive but this may be negative, right? Because F is a
Fraction.
no, it's a fraction, but it's still bigger. It's like sometimes it's
3 by
3 by 3, no? 3 by
But
2.
That's the
not-
answer, because it depends on V2 and V1. Some V2 and V1 it will be positive, some other V2 and V1 it will be negative, because it's like F plus 1 layer. So
No, but not because of F plus 1. Yeah.
But you also have multiplying.
No, but you know that A and B if you took, even if
from
you,
the graph we can't decide what is A and B. What
For
is the
different
relation
slopes
between
you
A
have
and B.
different.
For different slopes you can have a different answer.
correct. No, plus you have an F. No, basically if I had a 1 minus F, right,
Then you
I would have always said that, but it is F plus 1. So F is positive number. I mean 3 by 2, 1.5, so it's actually a reasonably big number. So it could be negative. So you can't figure it out. Yeah. Okay. So photoelectric effect was the last question. So we'll just do a little bit of photoelectric effect. Okay, so do you guys know how to do this question on, I'm assuming capacitors?
already 4 o'clock.
It's okay. It's okay. We'll just do it. We'll just spend another 10 minutes and then we'll stop. Okay. So do you guys know stuff on capacitor circuits, how to calculate and all that, right? Earthing and capacitors? Okay. So first of all, I'm assuming everybody knows that if I had a circuit, let us say some capacitor, some resistor and all that. Just cook up some numbers here, okay? So let us say we had some stuff like that. If there was one point which was earthed, what's the current through it? Zero. Because you can't have current going out of one point. But if I had two places that were earthed, it is the same as taking this point and joining it to that point, and after that you can put an earth here or there or anywhere in the middle. But now it doesn't matter because there's only one earth, so you can remove it. So now you have a system without any earthing, except that the charge could go like this, right? So therefore you can no longer conclude that it is zero current going out. So that's just something to keep in mind when you're solving some of the earthing problems. Okay, so let us do one, shall we do one question with circuits with earthing? Okay, do you have any of those questions? No, not this one.
You don't want this
I want the capacitor question.
capacitor questions.
These are all smarter guys, we should give them a lot of difficult questions. Well, this is not very difficult. So, a capacitor with earthing?
Yeah. Capacitor questions.
With earthing, huh? The earthing illiye.
No earthing questions with capacitors.
நான் ரெண்டு பண்ணேன் என்ன எழுதி வச்சுருந்தேன் earthing capacitor. சரி இந்தா just okay, so let us cook up one here. I have here a battery, a resistor, a capacitor,
That runs was a resistor.
This one, this is a resistor, that's a capacitor. And let us say that here I have a okay. Now I have these 3 points that have been earthed. This side there is no earthing. Okay. Right now just quickly tell me, what do you think, without doing any work, I have not yet put any numbers, right? Without doing anything, what will be the charge on this capacitor?
0.
Why?
It's not connected here.
Okay, so just think about this portion. These 3 fellows are connected, but there is no connection between this side and that side. So there is actually no current flow here. Because if anything flows, something has to get out. Which cannot get out and come back to this. No, just think of this blob. It is disconnected from there. Well, obviously, if I put a earthing here, then it's a different story. Okay? So now let us put 20 volts, 2 ohms. Let us say all these capacitors are C. So answer will be in terms of C. Okay, so this is 2 ohms, this is 4 ohms, and let's say this was 4 ohms. Okay, let's say this was 2 ohms, and that is 2 ohms. Okay, so what will be the charge on A, on B, on, well, this is X and that is Y at steady state. Try and do as quickly as possible mentally. A is 20C.
No,
No, 4
definitely not. There's some
That's a
current
4
flowing
ohm.
through.
There's current flowing through.
So don't be in a hurry, but do it as quickly as you can. Hmm? Just give me 1 second. Steady state, I want steady state, okay?
You won't get a round number. You will get 20 by 12 by 7 plus 2, 20 minus into C. This is what you get.
1 second, this is a 6 and that is a 10. 6 and 10 in
That's 10.
parallel. 6 and 10.
No. 6 and 8 in parallel.
6 and 10 in parallel. You have a 6
Yes.
and sorry, it is 6 and 8 in 6 and 8 in parallel. It's not, the 2 is not.
That 2 is not in the sound.
Okay, actually let me make this a little easier. I thought I'd so let us make this 2. Okay, just for calculation. Then it's easier. Okay, so 3 plus 2, 5. 5 plus,
Even then you will be getting some.
yeah. Shall I make that 5?
Hmm?
Shall I change that to 5?
5. Okay.
Okay. I'm just cooking up numbers, but so it's not great numbers, but just
16. Sorry, yeah, 16C
for which one?
on that A.
A. Okay. So this one is how much? Actually, just think of all these as one connected piece. You don't really need this earthing. You can connect all these fellows to the bottom. And you can get rid of this anyway, doesn't matter. Because there's only one earthing. Okay, so now if I look at this, there is no current here, there is no current there, no current here. So there is current flow here. So you can just remove these two fellows like open circuits in. So how much is this? 6. So this will be 6. 6 and 6 together, 3. 3 plus 2, 5. 5 plus 5, 10. So that means the current that's going to flow here is 20 by 10, 2 amperes. So when the 2 amperes comes here, this is going to be 5, right? Okay, so this is going to be 2 amperes into 5, which is 10. So that means there is a drop of 10. So this is 10 volts, this is 0. It is 0 because it's earthing. So it has to be 0. Okay, so if this is 10 volts, the charge on A, CA is 10 times C.
I took that 2 as 5. The next one.
Ah, okay.
So I got 4 drop there.
No, but you will end up with 2 amperes here
Yes.
and 2 amperes there.
1 ampere down.
There will
So-
also be a current through 20 volts and 0. This way.
Where is the 20 volts?
The battery.
Correct. That is this current. I mean, all this current has to go through the battery, right?
So will it, from there will it split up?
You mean from here?
Come here, this 2 ohms.
Yeah, this will come. I'll in fact calculate the current. Just give me a second.
1 ampere.
This is going to be 6 and that is 6. So this is going to be 1 ampere. That is going to be 1 ampere. This is 1 ampere. No current in here. Okay, so this is going to be 1 ampere. So charge on, sorry, this is not CA. Charge on A. Charge on B, well, this is potential drop of 2 times C. So this is 2 times C. Then charge on this fellow, well, that depends on this potential drop, which is 6, because this is 1 ampere. Okay, so this this potential drop is 6. So charge on X is 6C. And charge on Y will basically be 4C. So this kind of question you can easily do, right? So good. Then and switching, you know how to do switching. And everybody, I'm assuming, knows how to do. Like if I have an RC circuit, you know how to find tau, right? You know that all the answers are of the form A plus B e power minus t by tau. You know how to find tau? Tau will be what? Tau will be RC. So it will be RC. But how will you find RC?
R effective. C keeps
But basically take the battery and short circuit the battery.
Keep C same.
You don't need to do don't have to do Thevenin's theorem. I'm saying just simply short circuit this. Okay, if you short circuit Thevenin's theorem, basically you can replace. If you look at it from here, you can replace a set of batteries and resistors by one battery and one resistor in series. Okay, you don't worry about it. It's not required. Okay, this guy is just showing off. So instead, what you should do is suppose, okay, let us forget. Let's not have all this. Suppose I had. Okay, actually, let's say I don't have this. Let's say I don't have that. I don't have that. Now, if we look at this question, and you wanted to find out what will be tau. Like suppose I just wanted to switch this on. Forget steady state. At this point, I want to write down current as a function of time. That is the question. How will you go about it? First, or let's write, we can write current as a function of time, charge as a function of time, anything.
Just put the wire there instead of the battery.
Where?
Instead of the
First point is you start off by saying what is the current at time 0. And then you ask the question, what is the current at time infinity?
4 amps.
At time 0, why is it 4 amps?
Because it will capacitor is like a
It's like a wire, so this whole thing is like 0, so it is 20 by 5, so current at 0 is 4 amperes. Very good. What about current at infinity?
You have to consider that circuit.
So this is open.
So
This is how much? 6 plus 6, 3, 3 plus 2, 5, 5 and 5, 10, so it is 2 amperes. Okay, now I just want to find out what is tau, right? Tau is RC. Except how do you find R? Just short circuit this guy. So there is a 5 on this side, there is a 5 on that side. bring those two 5's together. So it is a 5 by 2. So it is 5 by 2c. Therefore, I as a function of time is a plus b e to the power of minus t by 5c2. This is the answer, except I need to find a and b. To find a and b, I don't need this part. If I put t equals 0, this will go away. And so I'll be left with a plus b.
If you put t equals 0, you'll have b.
Correct, a plus b. This will go away, means this will become 1. Okay, so this will be 4. And if I put t equals infinity, this will go away completely as 0. So you will become, I will be 2, and so a is 2. So therefore b is 2. And so answer is 2 plus 2 e to the power of minus 2t by 5c. Okay, so this you understand how to do this one. So you can quickly find out the time, basically find that infinity and 0 and then solve. Right, so what was that photoelectric effect? Okay, nothing much to do there. Okay, so just one second.
Yeah, something specific, right?
Did he ask anything specific? Can you read what he's asked?
A person called Harsh Rajkamal has asked a question.
Ah.
He is asking this question.
Who is that? Harsh Raj Kamal. Huh?
Yeah. Find the maximum value of B.
A parallel plate capacitor. So this is Harsh Raj Kamal's question. A parallel plate capacitor has circular plates.
Sir, he asked the difference between Einstein's approach and wave theory approach.
Okay, I'll explain that. Okay, so this has radius r 30 millimeters and plate separation of 5 into 10 to the power of minus 3 meters. Okay, so that is D. Suppose a sinusoidal potential difference with a maximum value of, so it is 150 sine omega t plus, okay, is already given. Maximum frequencies applied across the plates. So 150 sine 2 pi into 60. Okay, what is the B?
B. Maximum.
Okay, so this is applied across the plates.
Given frequency is 60 hertz.
Yeah. Okay, so how will you find B? What does Ampere's law say? Okay, first of all, why is there a B? There is actually an electric field here, right? And a changing electric field should produce a magnetic field. Right? So if I look at, suppose I try to find, so think of it this way. So changing electric field produces a magnetic field, but why is the electric field changing? Think of it this way. So there is some charge coming in and some charge going out. So it is like a current flow. Right? So how do we go about doing this? Let us see. That's basically what I'm doing. So I'm not going to use as Maxwell's correction. I'm just going to say Ampere's law. What does Ampere's law say? Integral B dl is mu naught I. Now we can use this. Okay, except what is I is the problem. Okay. I is this current. I can use it for any place, right?
We can also calculate the capacitance.
We can calculate the capacitance. So, but how does that help?
You can say Q is equal to CV.
And then?
From that get the current. dQ by dt.
You'll find the current there.
So you can use this V dot dl.
No, but what am I going to take as dl?
dl could be a circular arc. The surface, it should be a surface.
No, but this is over a.
Or probably you could use the differential form of
Correct. So, what does the differential form say actually? Forgot the differential form. What does the differential form say? dE by dt is curl of B.
D.
But I don't want to use curl of B. So let us. Ama.
What is curl?
Correct. அது கேப்ப தெரியும் வேணாம் விடு. No, but B max இல்லையா? So suppose I say I want this. If I assume that it is just outside this surface, because you'll have to use, if I use a surface like that, this is Ampere's law is true for any surface where I can choose my loop. So if I take this current that comes in will be how much? This is okay. So we'll write this as B into 2 pi R. Okay, I'm taking that as the loop. Okay, and how much is the current that comes in? Mu naught times, I'm going to take the current that comes in there. Because what Maxwell did was to say that, argue that the changing electric field is like a current. It's like what comes in is going out here, but is not going through this, right? So he basically proposed that it is equivalent of just that current. So I will take this loop and I'll take the current there. But do I know the current there? Well, I know the potential drop. So if because of the change in potential, so what is the charge? CV. Right, so current is going to be C times dV by dt. So what is C? Epsilon naught A by D pi R square. Let's write that as R square. So I'll write this as 2 pi R. Epsilon naught A by D, which is 5 into 10 to the power of minus 3, okay, into dV by dt, which is 150 cos of 2 pi into 60 t into 2 pi 60, so 120 pi. Is that correct? So if I want the maximum value of B, this I can just simply get rid of. Okay. Actually, this question should be what is the maximum value of B just outside the capacitor. Because if just outside the capacitor means you can make R, this will be the place. Because you can go inside the capacitor, I think.
The question is
Both should be
R
same.
is equals to R. Small r is equals to R.
The question says that,
Yeah.
but it didn't say.
Yeah, the question says that.
When you gave it to me, you didn't say that.
It's saying find the maximum value of the
Ah.
induced magnetic field that occurs at R.
Then it is simple. Otherwise, I was wondering what to do. Okay, now it's clear because otherwise I'll have to take all these parts. Okay, so now it's fine. But the problem is if I take these parts, it's still okay because it will turn out that it will be uniform. Because it will get split up. It's like a current density that is going in through. So then it is simple. Then it is quite simple. 120 pi. So full question, please. Half question, very dangerous. Okay, so now this 2 pi r we can cancel out with a pi and we can cancel out with the r, and then I have to cancel out a 2. So let us make this 60. So B max is, well, mu naught epsilon naught, do you guys know is
C square.
1 by C square?
1 by C square.
Right, you know that, right? Okay, so that means we can write this as 1 by C square. So it is R by C square into 5 into 10 to the power of minus 3 into 150 into 60 into pi. This C is a different C. This is speed of light C. What is R? 30 into 10 to the power of minus 3. Speed of light is 3 into 10 power 8. So this is 9 into 10 power 16. 5 into 10 power minus 3 and this is 6 into 90, 9,000 pi. It's a lot of messy numbers. So this is 5, 6, 9 is 1000. Okay, this is actually not so bad. So this is 6 pi 10 to the power of minus 13 Tesla. Not big B. This is the maximum B. Doesn't seem to be too large. Yeah, so this I think is the answer.
But he didn't give an answer.
He is not given an answer, but it's okay. So I think we did this right. So basically what are we using? We are using Ampere's law. Magnetic field here just outside B is going to be constant. So I'm taking a loop like that. So Ampere's law has a small problem, because the assumption is if there is current that comes in, okay, you take a cross section. You can take any shape, right? Because whenever you take a shape, if you took a shape that cuts it like this, you can actually say B around this is mu naught I through this. Okay, but the surface could be like that also. So I can take B there and the mu naught I there. It doesn't have to be a clear cut stuff like this. That's why the problem comes, because I can now think of a surface like this and a surface that goes that way. Here there is an I and there is a small B there. Okay. Now the problem was, if I had a capacitor, the current comes in and basically stops. And so I can take a surface like this and that goes around, and you can basically do this loop. Now if I cut it straight across, you know that this is the current. But if I go through this loop like this, there is no current anywhere, because the capacitor place has ended here. So the problem is then there is no current there. So no current goes through the surface. But you do have a magnetic field. You already know this is not zero, because if you did this, there is current. So you know that this is there is definitely some amount of current. So what Maxwell did was to say, well, if you took a surface here, whatever current comes in, when you do this, the same current goes there, but there is no current directly. So he called something called a displacement current. Okay, created something called a displacement current. Why does the displacement current occur? Because the electric field is changing. In fact, that was a huge discovery, because it was an entirely hypothetical situation. He continued from Maxwell's equation to figure out that if electric field changes, it is equivalent to producing a magnetic field. It's like a current. So changing electric fields can also produce magnetic field without actually any current. Was a very big jump, and that allows us to then have magnetic field, magnetic field progressing through whole of space, which then allows for light, because now in space there is no current flowing. You can just have an electric field that is changing, which will produce a magnetic field. So if electric field changes like this, magnetic field is produced like this. So if I now look at the magnetic field there, that is that, right, in that direction. Now the magnetic field is changing, but magnetic field changing will produce an electric field, because you already know that is Faraday's law. Okay, so now if magnetic field is changing in that direction, there is going to be an electric field produced in this direction. So I started with an electric field like this, with a magnetic field like that, and an electric field that way. Now electric field like that will produce, use your thumb, magnetic field like that. So you can see the magnetic field is perpendicular to the electric field, but it's continuously progressing, so that allows for electromagnetic waves. Okay, so this was the starting point of that discussion. Anyway, so yeah, like that. No, just one UN. No 5 more questions. Just UN's question about photoelectric effect.
Last question from
Akshay, okay. But let's just get to UN's question, okay? I don't know if UN is watching, but we'll get to his question. So his question was on photoelectric effect. So first point, suppose I take a string and I basically oscillate it. Let's get this point first and clearly. So if I did this, the energy is actually energy of these particles. These particles are jumping back and forth. So the particles had a mass m. That means when they go up, they're going to end up with potential energy, and at this point where they're coming back to this starting point, they end up having a kinetic energy. So the more they go up, the more is bigger the oscillation, more amount of energy. So the traditional wave theory, and it is generally correct, is if I had energy which was basically going to depend on the amplitude. Why does it depend on amplitude or amplitude square? Why? Because kinetic energy here is basically half Ka square. For simple harmonic motion, half Kx square, no, half Kx square. If you double the amplitude, you double the potential energy, which means you double the kinetic energy, you double the total energy. Huh? Sorry, correct. Oh, not double the amplitude. I said, okay. Correct. That's wrong. I mean, I said the exact wrong thing. Okay, I said if you double the potential energy, you will double the kinetic energy. But if you double the amplitude, this becomes 4 times. Okay, so amplitude is not directly related to the energy, but amplitude square is. Okay, in terms of relationship. So clearly, so amplitude determines the amount of energy in a usual wave. And light was thought of as an electromagnetic wave, which means if I had a high amplitude wave, and the assumption was intensity is the amount of energy that in a traveling wave, the amount of energy transferred is intensity. So if you increase intensity, that means you are increasing energy, which is correct. Okay, in general, intensity basically is related to energy. Now the problem here is more energy means you are supplying more energy, and so things must be able to absorb more energy. That was the assumption. But if I took a typical metal and you shine light, what happens is that you have electrons sitting in this metal, and these electrons don't jump off when you shine a lot of high intensity light if the frequency was very small. So if you took frequency less than nu naught, okay, so there was a minimum frequency, but people found that you shine a lot of light. Now a lot of light is a lot of energy. Okay, so this is a lot of energy, but the frequency is low frequency. So do you have enough energy? You have enough energy, but electrons are not coming out. Then on this side, let us say of the same metal, I basically shine less light, much less light. Okay, so that means much less intensity or much less energy, but I have a high frequency. Then it turns out electrons come out. So the question was, but you supplied so little energy and electrons are coming out. You supplied a lot of energy, electrons are not coming out. So what exactly is the problem? Einstein's argument here on how he resolved it was to say, yes, you are supplying a lot of energy, but actually the lot of energy is because you are supplying it in packets. You have supplied a huge number of packets, but an electron is going to be hit by one packet. So first packet that hits is like a small tiny thing, no effect. Second packet comes and hits, small effect, no effect. So 25,000 packets come and hit, but the electron can only absorb one of them. But all of them are very small, so it cannot actually absorb any of them. It's too small for it to escape. Imagine there are billions and billions of atoms coming and colliding with us, one by one. Now imagine all of them on this side are coming and pushing me, I will fly away. Okay, first of all, each one is coming and hitting me at a different time, which is actually good for us. If you look at whole day, atoms keep coming and hitting. If all of those atoms came and hit me at one time, the pressure on me would be too much. I'll get crushed. Whatever happens over a whole day, if it happens at one shot, it is going to basically be disaster. And if it all comes in one direction and it hits, basically I will fly off. Okay. Now, while there are there's a lot of energy that comes and hits, the energy is actually coming in packets. Each packet is very tiny. The electron requires this much energy. First packet comes and hits, electron doesn't move. Second packet comes and hits, electron doesn't move. Third packet comes and hits, electron doesn't move. Okay, but there may be like lots and lots and lots of these. It doesn't matter. In this case, what happens is each packet is this big, but you're only getting few packets. If you get one packet, this guy will fly away. So what matters is the packet size and not what is the total, because after all only one packet is going to hit an electron. First of all, electron is very tiny. It is not like 20 packets are hitting at the same time. One packet comes and hits, the other packet will hit another electron. Nobody is going to fly off. Whereas here, if you hit one electron, it will fly off. So that was the basic difference. So Einstein's point was, if suppose I had h nu, intensity is the total amount of energy supplied, but each packet is h nu. So intensity would be nh nu. So intensity is the measure of not the energy of one packet, but it is a measure of how many packets come. Energy of one packet is just simply h nu. Each packet must basically collide. Now this guy requires minimum amount of h nu naught. If you have h nu greater than h nu naught, one electron at least will come off. If you supplied n such packets, then n electrons could come off. So he called this the work function. So how much energy will the electron come out with? So imagine that this fellow is the photon with h nu. Now the electron, when it tries to go out, the rest of the metal will pull it back. Why? Think of it as a minus charge and a plus charge. By the way, that's actually a very nice electrostatics question. Suppose I had a metal piece. Do you know that if I had a point charge here, what will be the force of attraction of a point charge? How do you calculate? If this is a metal which is a large metal piece at zero potential, not charged.
Why should we experience anything?
Oh, because this will induce. No, it's a metal induction. So it will basically pull in a minus. It is equivalent to another piece here, which will be minus q. Exactly reflected. We can calculate it right now, we don't need to. So if I know that this distance is d, you can find out the energy that this guy will have. Or basically you can find out the force. So if I have to pull this guy off, remember it is like pulling this guy off also. So it is like 2 point charges that are trying to move away. So that will tell you that you need to pull off an electron or a positive charge. It is like creating a negative charge or a positive charge here, which is trying and grabbing you back. So work function is the energy required to pull that off. Okay. So now if I have to pull this off, it comes out with some kinetic energy, but it has already lost some amount of energy, which is the work function h nu naught. If it comes out with zero kinetic energy, h nu must have been equal to h nu naught. But suppose h nu was greater than h nu naught, h nu minus h nu naught will be the kinetic energy of the electron, fastest kinetic energy. Because some of them may not actually, they may lose more, they may collide, they may do other things. But if you look at bombarding it a lot, some of the fastest moving electrons, if you look at their kinetic energy, it will be this much, which is basically the work function here. H nu minus work function. Is that okay? So that hopefully should explain why your classical theory does not work. In the classical theory, you are assuming that if I increase the amplitude, which means I am increasing the intensity, I am increasing the amplitude, so I am increasing the energy, so electron should come, because the argument there was it's a wave that is coming in, and that wave is making this electron do all that, and so finally it will have enough energy to fly away. It's an electric field making electron jump up and down. But that is not how it works, it comes in packets. So it is like a particle coming and colliding with the electron and making it jump up. Okay, so that's how you should view it. And anyway, that's how today people understand electromagnetic interaction. That an electron and an electron exchange what we call virtual photons. So they throw a photon at this guy, and this guy throws a photon at it. So it is like a collision problem. So you can't understand.
If they come near, they will start throwing photons.
Even they are far away. But if I keep throwing photons and collect it back, so think of it like this. So if I was an electron, I throw a photon. If I throw a photon, I'll move that way. Then I'll throw a photon that way, I'll move this way. So I'll keep bombarding. I also, by the way, absorb back the photon. So these are called virtual photons. Okay, so it won't be at rest. It is like uncertainty principle, no? It won't be fixed. I send a photon, comes back. I throw a photon this way, come back. So it's jiggling around. Now imagine that there is another electron. I throw a photon, it goes there. Momentum conservation says that guy will start moving that way. That guy throws a photon, this guy will get it, and so this will move that way. So that is the idea of repulsion. Now you are throwing photons in all direction. So if I am at a distance r, the number of photons that will reach somebody there will be 1 by r square, which means the force between these two will basically vary as 1 by r square. Okay, so this is called quantum electrodynamics. People start with this idea and build the entire theory around it. No, this is a very, I mean, it's not, I'm not making this up. I'm saying this is a very good theory. It's in fact, Feynman's birthday. Feynman basically spent a lot of time on explaining how this works. It's a very good, it's a very good way of rethinking the entire particle physics. So we think of forces and then go to photons. Here, like for example, particles are actually carriers of force. So just turns around force at a distance. So photon actually is, we think of as electromagnetic waves. This fellow creates an electromagnetic wave, which is the photon. But this guy creates a photon, which is the electric field, which produces whatever we call the electric field. So think of it that way. Anyway, so this is not right now for us, but that is the basic idea. It started off with photoelectric effect. Okay, so what was the last question somebody had asked?
Akshay's question. And this is Akshay's question.
A spherical body of radius r consists of a fluid of constant density and is in equilibrium with its equilibrium under its own gravity. Under its own gravity in space. This must be in space. Under its own gravity, not by Earth. No mg. It's in space. Gm1 m2 by r square.
From what is the other
That's the other object is itself. It says equilibrium under its own gravity. Imagine that it's a spherical body, planet. A planet is in equilibrium under its own gravity. If P is the pressure at R, it's a spherical body of radius r. It is not, doesn't say a small drop of water. Okay, so this has radius r. It's in equilibrium under its own gravity. If P is the pressure at r, I think this is what is expecting, but pressure at r, then the correct option is, what is all that 63 by 80?
Sir, at R.
Oh, these are all the options, is it? Let us anyway calculate. At this point, gravitational force and pressure. So, okay, let us think about that. Where will the pressure be 0? Gravitationally, what is the force caused or created by these guys inside? You know that a shell doesn't cause any force inside, right? Okay, so let us
What gravitational pressure is at that point?
yeah.
3 by 8 by.
That's what I'm going to do. I'm just going to say, if I'm thinking of a thin layer,
You have to integrate.
if I think of a thin layer, okay, now this pressure difference for the thin layer, delta P. So if I call this P at R, this will be P at R plus dr.
So instead of doing like pressure difference,
You have to integrate, there's no other.
what is the question asking us?
What is the pressure at various points?
So we can't like let's just take the pressure like gravitational force divided by the area and then integrate that one.
That's what I'm going to do.
So
Okay, let me just calculate now. I've just read the question. Just hold a second. I'm just saying delta P. So dP. Okay, which is going to be higher? This is going to be higher. So dP into 4 pi r square. 4 pi r square is the force outward. Okay, and that must basically match the force inward due to gravity, correct. Or we could look at, no, that is a force by whom? Gravitational force by whom?
The outer block, all the above of the outer block
Huh?
on the inner block.
All the above molecules.
See, whatever is within the sphere
Huh?
will attract the shell. Other way is not true. The shell does not attract the.
So all these fellows will actually pull that shell in, right?
Is that correct? Or
That is correct. These guys won't pull the shell. So the mass here is going to pull that shell. So, what? Why does it violate? This will pull that in all directions. So net force on it is 0 anyway. It's only pressure, right? So if I take so let us think about the gravitational field here into that mass will be the force inwards, right? This is the outward force. Well, I'm saying outward pressure actually. Okay, so what is the force here? Gravitational force. What is the mass? You can think of this as a total point job. So it is 4 by 3 pi r cube. Was the total mass given or something? Density is given? Fluid of constant density is given. Okay. So let us say rho. 4 by 3 pi r cube rho is the mass of this fellow. So G m by r square will be the force effect field there into 4 pi r square dr into rho. G m1 m2. Okay, and that must be equal to dp by 4 pi r square. So I'll just divide it by 4 pi r square. Okay, I think that I might have to put a minus sign somewhere, but let's just anyway calculate. Let us do this. This is an r. So this gives 4 pi by 3 g rho square r dr. So if I did an integral from 0 to r. But the pressure at the center is the largest, right? Pressure, why is the pressure at the center the largest? No, pressure at the center is 0. Because a point particle here does not have two. No, at the center the force is 0, no? Nobody outside is pulling. Pressure at the center is 0. It looks like it should be the highest pressure, right? That's what I'm also thinking.
At 0.
Huh.
At 0 it should be 0.
No, the force must be 0, but why should the pressure be 0? Hold on.
Because 0 area.
I know that the pressure outside at the topmost point is 0, right? Actually, why don't we go from R to infinity, R to capital R? So if I go from R to capital R, okay, so this one is some constant. So let's call that K. By 2 also we'll take it and put it as K, R square minus R square. And this is pressure at R minus pressure at R. So minus, so pressure at R is K times R square minus R square. Okay? But the only problem is I feel this is not correct. I should have put a minus sign here, because this way we are assuming that the pressure inside is higher. So this should be this way and that pressure direction is that way. I should put
Itself, force will be minus G.
Correct. So I'll just arrange for R square minus R square. Okay, so now what is the question? Pressure at R equals 0 is 0 is not correct. Okay, actually with a simple fact, center of the earth, the pressure is very high, right? So you don't expect it to be 0 because it's all kind of compressing. You don't expect at the center it should be 0. So clearly that one is not correct. Pressure at 3 by 4R. So let us try this. So P 3R by 4 by P 2R by 3 is question, right? So the K will cancel out. So this is r square all will cancel out. So it will be 1 minus 9 by 16 by 1 minus 4 by 9. Okay, so 4 by 9, right? So 16 minus 9 is how much? 7 by 16, and this is how much? 5 by 5 by 9, right? So by 5 by 9, correct? 63 by 80. Okay, so that is the option that is given. So this one is correct. Option B is correct. Okay, and then they have asked something about P of 3R by 5 by P of, was multiple options correct or only one? Multi-correct. So 1 by 9 by 25, 1 minus 4 by 25. Okay, the 25 at least will cancel. So this is 16 by 21. Okay, so this is also correct. And then you have P of R by 2 by P of R by 3. 1 minus 1 by 4 by 1 minus 1 by 9. So that is what? 4 minus 1, 3 by 4. This is 8 by 9. So this is 8 by 9. So 27 by 32. That is not right. P of 0 is wrong. So this is correct and that is correct. So B is correct, C is correct. Okay, so we will stop now. So, okay, so all the best for your BITSAT and your IIT entrance. Do well. No, tomorrow. No, tomorrow I have to run somewhere. But we'll continue discussing on the app.